The Andromeda Galaxy, with its 1,000 billion stars, is often considered the twin sister of our Milky Way. Measuring 220,000 light-years in diameter, Messier 31 is a huge celestial object, the furthest from Earth that can be observed with a naked eye under clear skies, even though it is 2.5 million light-years away. The first observations of this luminous spot go back to the dawn of time, but the first written records date back to 964. They are due to Al-Sofi, a Persian astronomer. The Andromeda Galaxy, located in the constellation of the same name, is easily recognized by its oval and diffuse shape with a bright core. The latter, of yellow color, contrasts with the dark dust bands and the large arms that trace their way around. This is a spiral galaxy, the closest to our galaxy, which offers us a breathtaking spectacle. In its meanders, we can see clusters of blue stars, but also nebulae of reddish color. The total mass of the Andromeda Galaxy, estimated at 1,230 billion solar masses, against 1,900 billion solar masses for the Milky Way, does not prevent it from containing a considerable number of stars more. In the heart of its bowels is a supermassive black hole, estimated at 140 million solar masses, which is much larger than the one in our galaxy, which is estimated at only 4 million solar masses. Andromeda has two companions, Messier 32 and Messier 110, both of much smaller size. The first, Messier 32, is a compact elliptical galaxy, its greatest length not exceeding 8,000 light-years. Distant from the Sun by 2.5 million light-years, it is an elliptical dwarf galaxy, with a mass of only 3 billion solar masses. Although it may seem insignificant, it contains a central bulge whose characteristics are comparable to that of its host, M31, with a mass of about 100 million solar masses. It is estimated that approximately 5,000 stars per cubit parsec are rapidly rotating around a central supermassive object. It is mostly composed of old stars and has a high surface brightness. All indications are that Messier 32 was once much larger, but that its outer star population and globular clusters were considerably absorbed by its giant host, the Andromeda Galaxy. But what about this giant second companion, Messier 110? Is it as impacted by its proximity to the Andromeda Galaxy? Like Messier 32, it is an elliptical dwarf galaxy, which does not appear to contain a supermassive black hole. Its diameter is 17,000 light-years, twice that of Messier 32. It is smooth and almost featureless, with no arms or star-forming regions, but it does contain a population of young blue stars in its center. There are 10 billion of them, as well as 8 globular clusters that are visible in its halo. As you can see, Messier 110, unlike its companion, does not appear to be at the end of its activity. These three cosmic monsters are far from evolving alone. The Andromeda Galaxy and its two smaller sisters are accompanied in their astral dance by many smaller galaxies. These form the subgroup of Andromeda. There are at least 14 dwarf galaxies that belong to the Andromeda Galaxy subgroup. Of course, there is Messier 32 and Messier 110, whose discoveries date back to the 18th century. But since the 1970s, new galactic objects have been discovered, one after the other, thanks to technological advances. Thus, the galaxies Andromeda 1, 2, and 3, all distant between 2.1 and 2.4 million light-years from our Sun, were discovered in 1972 by Sidney Vandenberg, a Canadian astronomer. This scientist also discovered Andromeda 4 at the same time. If he believed at first that it was an irregular galaxy belonging to the subgroup of Andromeda, the measurements made in 2000 with the Hubble Space Telescope place it rather between 16 and 26 million light-years. This galaxy would then be largely outside the local group. In 1998, the galaxy Andromeda 5 joined the subgroup of spherical dwarf galaxies of Andromeda. It is 2.6 million light-years away from our solar system. Also in 1998, it was the turn of the spheroidal dwarf galaxy of Pegasus, or Andromeda 6, and the dwarf galaxy of Cassiopeia, Andromeda 7, to be revealed. The distance of the former is still poorly defined, but it could be between 2.5 and 3.1 million light-years, while the latter is estimated at 2.5 million light-years. We will not continue this list, which extends to Andromeda 33, a dwarf galaxy of the same type as its consorts and discovered in 2013 thanks to the Pan-STARRS-1 astronomical survey program that uses a panoramic survey telescope and rapid response system located on the Hawaiian archipelago. Among the main members of the local group, other cosmic monsters, although less imposing, are just as marvelous and reserve us an extraordinary show. This is notably the case of a duo of dwarf galaxies, separated by only 75,000 light-years. These are the famous Magellanic Clouds. These two galaxies, very close to our galaxy, are remarkably visible to the naked eye from the southern hemisphere, appearing as two milky spots in the deep sky and resembling fragments of a cloud of stars that would have broken away from our galaxy. It is not known when the first observations of these two celestial objects date back to, but it is in 924 that the Large Magellanic Cloud is described for the first time in the literature by the Persian astronomer al-Sufi, even if their identification was formalized during the voyage of Ferdinand Magellan in the 16th century. But what makes these two galaxies even more curious is a kind of bridge that seems to connect them to each other. Let's get a little closer to this strangeness. Let's start by observing the Large Magellanic Cloud, which is a dwarf galaxy of the barred spiral type. It is located in the constellations of the Dorado and the Table. Its disk shape is characterized by the presence of a single spiral arm and a large bar that were discovered long after the galaxy itself, which explains why it was first catalogued as an irregular galaxy. The Large Magellanic Cloud is 163,000 light-years distant from our solar system. But more importantly, it occupies the 4e position in the local group in terms of mass, after the Andromeda Galaxy, the Milky Way, and the Triangulum Galaxy. Several 100,000 giant and supergiant stars are counted there, as well as 60 globular clusters, 400 planetary nebulae, and 700 open clusters. Among the very many celestial objects it contains, we can note two high-mass stellar black holes, both in the form of binary systems. We can also observe a soft gamma-ray booster, the first object of this type to be discovered. It is a source of gamma rays with violent and recurrent episodes of emission, but regular and most probably corresponding to young neutron stars with intense magnetic field. One of the youngest pulsars, probably about 1,650 years old, with a rotation period of 50.3 milliseconds, can also be seen. These last two objects are both located in the aftermath of supernovas, these explosions of stars that give us a show of beauty. We can thus see that an intense activity reigns in the interstellar median of the Large Magellanic Cloud, where the quantities of gas and dust are colossal. This explains why an important quantity of new stars emerge in its heart. The largest and most active region of the local group is the Tarantula Nebula. This galaxy is the most active of any region in our galaxy and has a star birth rate like no other. In fact, the Tarantula Nebula is the largest nebula known to date. But what makes the Large Magellanic Cloud so special is the link it has with its fellow traveler. Indeed, the southern bar of the Large Magellanic Cloud is connected to the Small Magellanic Cloud by a bridge of gas and stars, known as the Magellanic Bridge. This structure, which is due to the tidal forces linking the Magellanic Clouds, and perhaps also to those of the Milky Way, is mainly composed of neutral hydrogen. However, it is home to a few stars that must have formed within it. The Small Magellanic Cloud is an ancient barred dwarf spiral galaxy, which has become an irregular galaxy due to the inexorable tidal forces around it. Distant from our Sun by about 200,000 light-years, its diameter is half that of its big brother, reaching 7,000 light-years. For those who have the opportunity to observe it from the southern hemisphere, it occupies in the night sky the value of 10 full moons, which made it, in the first Polynesian or Australian Aboriginal cultures, an indispensable tool for navigators. This visibility to the naked eye is mainly due to its small distance from our Sun, although it is one of the most distant objects that can be observed without instruments. If the Small Magellanic Cloud is considered small compared to other galaxies, it would nevertheless contain no less than 3 billion stars. We can also admire in the heart of this small galaxy many objects all more luminous and colorful than the others, including star clusters that shine brightly, supernova remnants, or magnificent nebulae, where the occurrence of new stars is particularly intense. Let's move on to the third galaxy of the local group, the Triangulum Galaxy, also known as Messier 33, which lies in the northern constellation of Triangulum. Located about 2.7 million light-years from Earth, it is over 50,000 light-years in diameter and hosts more than 40 billion stars. It is a regular spiral galaxy, which means that it is unbarred. Without rings, it is in the form of a galactic disk that surrounds a central bulge. The mass of this galactic monster is estimated at 60 billion solar masses, which is still far less than our Milky Way and the Andromeda Galaxy, which are both at the top of the podium in terms of size. Messier 33 represents only 5% of the mass of the Andromeda Galaxy, estimated at 1,230 billion solar masses. The Triangulum Galaxy is very different from the Milky Way, which you have certainly visited. It is larger, flatter, and brighter. It also has a large number of spiral arms, rather open, each containing billions of stars and gas clouds. the absence of significant interaction of this galaxy with other massive objects allows it to maintain its beautiful spiral structure, a relatively symmetrical overall shape, and therefore does not experience major alterations. Like its larger sisters, it has a large amount of gas and dust, which makes it an ideal place for the formation of stars and planets. As you travel through the Triangulum galaxy, you can see many types of stars, including red dwarfs, red giants, binary stars, and massive stars. In fact, astronomers count more than 500 active regions of infrared radiation that are massively concentrated in its center and along its spiral arms. Among the brightest regions of the galaxy are its main nebulae, NGC 588, NGC 592, NGC 595, and NGC 604. The latter, also called the Triangle Nebula, is the brightest of all and extends over nearly 1,500 light-years. It is the second most luminous region of ionized hydrogen in the local group. Thanks to the Hubble telescope, we know that it hosts about 200 young and hot stars distributed in at least 2 clusters. Their masses vary between 15 and 60 solar masses. Moreover, it is in the southern spiral arm that the rate of explosion of supernovas is the most important. There would be, on average, every 147 years, which explains the 100 of supernova remnants that could be identified there. There are also many other interesting phenomena, such as jets of matter, expelled by some supermassive black holes. In summary, the Triangulum galaxy is a place full of discoveries and wonders of nature. It's an incredible sight to see, isn't it? Among the main members of the local group, I invite you to discover now NGC 185 and NGC 147, 2 galaxies that belong to the great majority that compose the local group, namely the dwarf spheroidal galaxies. However, as you will see, these 2 dwarf galaxies have a small peculiarity, apart from belonging to the Andromeda subgroup. Let's start with NGC 185, a dwarf spheroidal galaxy located about 2.1 million light-years from our Sun. It is remarkable for its small size and low mass, which is approximately 1/10 that of the Milky Way. If, like all galaxies of this type, it contains few stars and gas because of its advanced age, on the other hand, its surface, of a very high luminosity, and its extremely bright and compact nucleus place it in the category of Seyfert galaxies of Type 2. This type of nucleus represents one of the largest known sources of electromagnetic radiation in the universe. Would it hide a supermassive black hole in its center? Therefore, it arouses our curiosity, especially since it displays a notable proximity to a neighboring galaxy, NGC 147. Like its companion, NGC 147 is a dwarf spheroidal galaxy, located about 2.2 million light-years from our solar system. It also contains few stars and gas, but what makes it intriguing is its particular location near its neighbor. It seems that these 2 galaxies form a gravitationally stable binary system. These galaxies may not look as impressive as the large spiral galaxies, but they are interesting to study because of their interaction and proximity, especially since a third object, the recently discovered pale dwarf galaxy, Cassiopeia II, may also be part of the satellite system of the Andromeda galaxy. It may well be that these three galactic objects are part of the same cosmic dance. But to confirm this, we will have to examine their choreography for some time. Let's continue our exciting journey through the Barnard Galaxy. This galaxy is shyly located in the constellation of Sagittarius, about 1.5 million light-years from the Milky Way. It hides its irregular shape behind a screen of dust and closer stars, which explains why it was only discovered in the 1880s by Edward Emerson Barnard. Its appearance is not unlike that of the Small Magellanic Cloud, is it not? Its largest diameter reaches 7,000 light-years, and although it does not shine like the biggest divas of the local group, it is full of young blue stars. Although it does not have splendid spiral arms, it is surrounded by a necklace of purple nebulae, where intense activity heats the surrounding hydrogen during star formation. As a proof, we can sometimes see a brood of massive stars that ejects with an unheard of violence the matter, literally blowing the interstellar gas. This small galaxy has nothing to envy to the larger ones, showing signs of an obvious star formation activity. Let's visit the last of the main members of the local group, the galaxy named IC 1613. Located in the constellation of Cetus, the sea monster, and distant a little more than 2.3 million light-years from our Sun, we owe its discovery to the German astronomer Max Wolf in 1906. But it was in 1928, using a powerful 2.5-meter or 8-foot telescope at the Mount Wilson Observatory, that his compatriot, Alter Bod, successfully visualized its individual stars. Once again, this is a dwarf galaxy with low surface brightness. But our journey to it is not by chance. This galactic neighbor, unlike its fellow galaxies, has made a clean sweep. What we want to explain to you is that it contains very little cosmic dust, allowing it to reveal the wonders it contains. This phenomenon is quite rare, and therefore worth observing. No dark trail of sidereal dust, opaque and swirling, is visible among the gas and stars that populate this galaxy, which appears clean as a whistle. Two types of stars can be seen, pulsating at their own pace: Cepheid variables and RR Lyrae variables. Because of its unusual appearance, the IC 1613 galaxy offers great opportunities for observations. Despite its small size, it has helped scientists to understand and use variable stars to map our universe. So it is not the largest objects that hold all the keys to the cosmos. I now propose you to visit the dwarf spheroidal galaxies which compose the subgroup of the Milky Way, and to which they are gravitationally linked. They can be observed in this small corner of the universe, within a radius of 1.5 million light-years around our galaxy. Let's start with a huge galaxy that has been hidden for a long time behind the galactic disk of the Milky Way, in the constellation of Antlia, at a distance of 422,000 light-years. Its existence was detected in 2018 by the Gaia satellite. Let me introduce you to the Antlia 2 galaxy. This galaxy, with nearly 9,500 light-years in diameter, is relatively similar to the Large Magellanic Cloud, but unlike the latter, its brightness is 10,000 times less. It even appears 100 times more diffuse than the so-called ultra-diffuse galaxies, whose luminosity is very low, making it the least luminous of all the galaxies known to date. This characteristic is also the reason why it is called a ghost galaxy, although its size is 1/3 of that of the Milky Way. In short, it is a galaxy that is either too dark for its size or too large for its brightness. One of the most interesting features of Antlia II is that it is also rich in dust clouds, which are regions where new stars and planets form. These dust clouds are visible due to their absorption of light from the background stars, forming dark regions called dark dust clouds. Antlia II is rich in young stars and gas. This means that there are many new stars forming in this galaxy. In fact, it is estimated to be about 10 times more active in star formation than the Milky Way. Therefore, as you can see, there are many star clusters in Antlia II. These clusters are groups of thousands of stars that have formed together from a single cloud of gas. Some of these clusters are very young and still contain stars in the process of forming. Another particularity is noteworthy. Its mass appears well below the first estimates made on the basis of its size. Could it be the consequence of incessant dismantling caused by the galactic tides of the Milky Way? Moreover, this galaxy, whose age is about 11.2 billion years, raises another problem for scientists: a problem of size. In theory, galaxies that are devoured by another galactic monster see their size reduced. Antlia II is huge and seems to be growing rather than shrinking. It seems that this phantom galaxy has not yet revealed all its secrets, which makes it even more fascinating. Another galaxy is the talk of the scientific community. It is the Sagittarius dwarf galaxy, which has been the subject of debate since its discovery in 1994. It is considered by some as a spheroidal galaxy and by others as an elliptical galaxy. Be careful not to confuse it with the irregular dwarf galaxy of Sagittarius. About 10,000 light-years in diameter, it is approximately 50,000 light-years from the center of the Milky Way, which makes it also one of its satellites. Its population of old and metal-poor stars makes it possible to establish that it is an old galaxy, especially since it has little interstellar dust. We can think that it was at the base of a dwarf spheroidal galaxy, which would have suffered the consequences caused by tidal forces of the Milky Way, especially since a significant number of its stars and a stream of gas appear scattered throughout its orbit. Moreover, the dwarf galaxy of Sagittarius seems to disturb intermittently the outer disk of the Milky Way, to which it is a little too close since 5 or 6 billion years, producing numerous filamentary structures. If at the moment of these structures of filamentary and spinning appearance are not yet explained by astronomers, several theories are emerging. In particular, that of the remains of fossil spiral arms. Whatever the case, these structures are certainly related to past interactions with the Milky Way. The interactions between the Sagittarius dwarf galaxy and our galaxy are not going to get any better, since its trajectory indicates that it should cross the Milky Way galactic disk within 100 million years. It will thus probably be absorbed entirely by our galaxy through a long process of destruction and restructuring. In the category of spheroidal dwarfs, we can continue our journey towards the Dragon dwarf galaxy. Located in the constellation of the Dragon, at about 260,000 light-years from the Earth. Its discovery dates back to 1954 by Albert George Wilson of the Lowell Observatory. It is globular in shape and extends from 2,700 to 1,800 light-years, making it one of the smallest galaxies known. It is also very faint in terms of luminosity. It is one of the least luminous companions of our galaxy. This object that orbits our galaxy also seems to contain large amounts of dark matter, this mysterious matter, still hypothetical, and whose existence has not yet been proven directly. It has thus become an ideal candidate for the scattering phenomenon and could be very useful for scientists working to understand cosmic mechanisms. However, more than 260 variable stars accumulate at its center, and despite its small size and luminosity, the Dragon Dwarf Galaxy is rich in old stars and metals such as iron, calcium, and magnesium. The ancient stars probably formed billions of years ago. The presence of these old stars and metals indicates that the Dragon Dwarf Galaxy has experienced a lot of star formation activity in the past. It also contains several red giants, which are low-luminosity stars. These stars have exhausted their nuclear fuel and consequently have stopped shining. These stars are very enriching because they contain information about the history of the galaxy. They are also potential candidates for the search for extrasolar planets. Who knows, maybe one day we will be able to detect the presence of potentially habitable planets in this region of the cosmos. Among other deep sky objects, we can also explore the dwarf galaxy of the Little Dipper, which can be reached in the constellation of the same name. Its average distance from our Sun is 205,000 light-years, while it is only 1.4 million light-years from the center of the local group. Its size, 45 times smaller than the Milky Way, is estimated at 2,200 light-years. Discovered under the same conditions as the Dragon Dwarf Galaxy, the findings seem identical. It is similarly a galaxy that could contain a large amount of dark matter. Indeed, the velocity dispersion does not decrease with the distance to the center of the galaxy. Moreover, 94 bright stars have already been identified in the bowels of this object, whose radial velocity brings it closer to our solar system at a speed of 247 kilometers per second, or 153 miles per second. This is a new galaxy with many suns, which seems to be expanding. Do you think that it may have a few planets where extraterrestrial life could have developed? And why not? But do you know which is the first dwarf galaxy that was discovered orbiting the Milky Way? Well, it's the Sculptor Dwarf Galaxy, first described in 1937 by astronomer Harlow Shapley. Since then, many other observations have been made, notably thanks to the Gaia study of the European Space Agency and observations made with the Hubble Space Telescope. The galaxy has, among other things, allowed scientists to determine how individual stars move through a galaxy of this type. They are now able to confirm that their change in position is tiny, even over long reference periods of about 10 years. The proper motions of about 100 stars have been measured, and coupled with the radial velocity, the motion of the stars could be reconstructed in 3 dimensions. This is the first time that such a reconstruction could be performed for a dwarf galaxy. The Sculptor Dwarf Galaxy thus plays a crucial role in the astronomer's sphere, who can now study the impact that the gravity of dark matter, this elusive matter, can have on the motion of other objects, such as stars or galaxies. Let's now take the direction of the Sextant constellation, where the 9th satellite of the Milky Way is hidden, the Sextant Dwarf Galaxy, or Sextans 1. This galaxy, of spheroidal type, was detected in 1990 by Mike Irwin as part of a comprehensive sky survey plate monitoring program, United Kingdom Schmidt Telescope, with the application Performance Monitoring Measurement Machine in Cambridge, UK. The distance of this object is estimated to be only 280,000 light-years from the Sun. Its apparent magnitude is 10.4, which makes it one of the least luminous galaxies among the closest to our Milky Way. As you can see, it is also an elliptical galaxy, with a redshift as it moves away from us at a constant speed of 224 kilometers per second, or 140 miles per second. It is small, and its diameter measured along its main axis does not exceed 8,400 light-years. As you can see, its population consists of old stars poor in metals. The in-depth study of this galaxy allows us to question the hierarchical formation scenario. This theory, according to which galactic monsters such as our Milky Way would have been created mainly by absorbing other galactic objects over time, cannot be affirmed when we study more closely the chemical composition of the dwarf galaxies that surround it. Indeed, compared to our galaxy, Sextans 1 presents a deficit of the most primitive stars. This indicates that the fossil content of the primitive epochs, the epoch that precedes the assembly of galaxies between them, is not similar. Thus, neighboring dwarf galaxies do not have the same characteristics as the halo of our Milky Way, its oldest part. Moreover, the Sextant 1 galaxy, like many other galaxies of the same type, lacks very low iron stars, unlike our galactic halo. Here is another dwarf spheroidal galaxy, the Carina Dwarf Galaxy, also named PGC 19441. It is found in the constellation Carina. This satellite of the Milky Way is about 330,000 light-years away, but is gradually moving away at a speed of 230 kilometers per second, or 140 miles per second. Its size is estimated to be 75 times smaller than our galaxy, with a diameter of 1,600 light-years. It is part with the Lion 2 galaxy of the smallest known galaxies. It is home to a majority of stars whose formation dates back approximately 7 billion years, which means that they appear less ancient than those of other satellite galaxies. The Carina Dwarf Galaxy may be more recent than its twin galaxies, although it has also experienced other peaks of star formation, notably 13 and 3 billion years ago. Another satellite galaxy of the Milky Way attracts our curiosity, this time in the constellation of the Furnace. It is the dwarf galaxy of the Furnace. Distant from 450,000 light-years from the Sun, it is, like almost all nearby dwarf galaxies, composed mostly of old stars, called Population 2. It has a recession of 53 kilometers per second, or 33 miles per second, moving further and further away from our Milky Way. Its low surface brightness makes it unattractive at first sight. However, it contains several treasures, including a planetary nebula and 5 globular clusters, the largest of which, named NGC 1049, was discovered a century before its host by the British astronomer John Herschel in 1835. This cluster contains a large number of stars, which makes it brighter than the galaxy itself. As proof, its distance of 444,000 light-years does not make it invisible with a medium-sized telescope, unlike the galaxy that hosts it. This cluster and its companions have been the subject of numerous observations. It appears that they are very similar to those existing in our Milky Way. This observation challenges the main theories on the formation of these clusters, which should be surrounded by large quantities of old stars. However, we see that this is not the case here. As is often the case in astronomy, a new observation, even if it opens a little more the door of our knowledge, puts in question some theories, leading to new questions. Let's now look at the last 2 spheroidal dwarf galaxies belonging to the Milky Way subgroup, the Leo 1 galaxy and its twin, the Leo 2 galaxy, also named Leo 1 and Leo 2. Their simultaneous discovery is attributed to Robert Georges Harrington and Albert Georges Wilson in 1950. Like the Carina galaxy, their diameter does not exceed 1,600 light-years, which makes them the smallest known galaxies of the Milky Way subgroup. The first, the Leo 1 galaxy, is 800,000 light-years away from our Sun. The second, slightly closer, is 700,000 light-years away. The latter is made up of stars 8 billion years old. It does not produce any more new stars, except in the center, where we can see younger stars. Leo 1, however, has captured the attention of researchers since it was found that it contains a relatively small amount of dark matter compared to its peers. It was in 2021 at the McDonald Observatory, and with the help of a supercomputer, that a team from the University of Texas discovered that a supermassive black hole, namely of 3.3 million solar masses, reigns at the heart of the Leo 1 galaxy. Here is yet another mystery to be solved. How can a black hole of this mass exist in such a small galaxy? We have just visited the dwarf spheroidal galaxies belonging to the Milky Way subgroup. However, there are other dwarf spheroidal galaxies that are labeled as ultra-faint. If you want, let's go to meet them, while staying in the constellation of Leo. The discoveries follow one another thanks to new technologies and numerous programs. The Sloan Digital Sky Survey, or SDSS for short, is a celestial object survey program using a dedicated 2.5-meter or 8 feet diameter optical telescope located at the Apache Point Observatory in southern New Mexico, USA. This program, which started in 2000, has allowed to count in 2006 about 24 dwarf companion galaxies of our Milky Way, whereas half of them were counted until then. One of these galaxies, named SEG-1, is 75,000 light-years distant from the Milky Way. 1 billion times fainter than our galaxy, it appears to be composed mainly of dark matter, with only a few hundred stars scattered in its bowels. SEG-1, despite an extremely low luminosity, which does not exceed that of 300 suns because of its practically insignificant number of stars, is considered as a dwarf spheroidal galaxy. Its mass corresponds to about 600,000 suns, which is too large for a globular cluster, especially since its stars are rather similar to those usually found in galaxies. This lack of luminosity, associated with a very compact structure and a low concentration of metal, seems to indicate that this is a very old celestial object, which will probably have encountered, during its cosmic wanderings, the gravitational disk of our galaxy. But what remains a mystery is the mass of this object, which cannot be explained by the presence of a black hole. Indeed, the stars present do not swirl ardently around an object that would be massive. Consequently, Seg-1 does not have a massive black hole in its center, which could explain this important mass. No other matter in sufficient quantity like hydrogen gas, in astronomical accumulation, or dust can explain this mass. Seg-1 would thus be the only dark matter galaxy in the universe. A little further away, another galaxy was discovered during the same study program, Sloan Digital Sky Survey, in the Aries galaxy, the Seg-2 galaxy. Located at about 114,000 light-years from the Sun, this small galaxy is approaching our Sun at a speed of 40 kilometers per second, or 25 miles per second. Its stellar population is composed mainly of old stars, formed more than 12 billion years ago. No newly formed stars are present. Their metallicity is very low. They would contain at least 100 times less heavy elements than our Sun. You are probably looking at the oldest stars in the universe. Seg-2 contains only 1,000 stars and some dark matter that binds them together. Its luminous power is strongly impacted. It is barely 900 times brighter than the Sun, which is ridiculously low compared to the Milky Way, which shines 20 billion times brighter. The Seg-2 galaxy is thus one of the faintest galaxies known to date, weighing at least 10 times less than previous estimates for such objects. This is a new challenge to the theoretical understanding of structure formation in the universe. Let's now visit the Great Dog Dwarf Galaxy, which is our closest neighbor and is located on the periphery of our solar system. It is about 25,000 light-years from the Sun and 42,000 light-years from the center of the Milky Way. It is located, as its name suggests, in the constellation of the Great Dog. It is a small, irregular galaxy whose mass is equivalent to nearly 1 billion solar masses. Long hidden behind the plane of the Milky Way, hidden by the dust and gas trapped in its disk, it was discovered only recently. It is thanks to an infrared survey, allowing astronomers to see many regions of space well beyond the disk of our galaxy, that it was detected for the first time in 2003, dethroning then the dwarf galaxy of Sagittarius of its status of closest galaxy. Rather elliptical in shape but irregular, it is home to 1 billion stars, including a large number of red giants, which in fact represents only a small percentage compared to the Milky Way. Its main body, of jagged and fragmented appearance, is thus of irregular shape. This degradation seems to be the consequence of the accretion to the Milky Way that it inexorably undergoes. Undergoing the tidal forces of the latter, it is literally torn apart, leaving in its wake a long filament of stars. It is so long that it goes 3 times around the Milky Way, taking the form of a ring known as the unicorn ring. it looks like there are other remnants that have not yet been completely swallowed up. There are several globular clusters which have been discovered in different constellations: the Dove, the Hare, the Stern, and the Carina, and which would have been separated from their host. I propose you now to join the constellation of the Great Bear, this immense constellation which decorates our starry sky with a famous Big Pan. Adorned with countless stars, it is home to a magnificent planetary nebula. But above all, there are no less than 50 galaxies, including the Big Dipper 1 galaxy, also called Ursa Major 1. This galaxy, with low surface brightness, is 316,000 light-years away from our Sun. It is one of the 3 least luminous galaxies recorded to date. In comparison, it is less luminous than the star Deneb, which is in our Milky Way. It is made up only of population 2 stars, that is to say, old stars with low metallicity. You can find similarities with the dwarf galaxy Sextant 1. It is, like its cousin, old and poor in metals, and measures only a few thousand light-years in diameter. Let's take the opportunity to visit the Great Bear 2 dwarf galaxy, also known as Ursa Major 2 or UMA 2. Discovered at the same time as the previous galaxy, it is about 30 kpc from the Sun, or about 97,800 light-years. Its luminosity is about 4,000 times that of the Sun, which is well below the vast majority of globular clusters that we can admire. It is even less luminous than some stars in our galaxy, such as Canopy, for example. The majority of the stars in this galaxy are population 2 stars, that is, stars of advanced age. The formation of these stars probably dates back to more than 10 billion years. Their relatively low metallicity index is estimated at more or less 0.06, which means that they contain 300 times less metal than our Sun. However, its total mass is equivalent to nearly 5 million solar masses, if we count baryonic matter and dark matter. Its mass to luminosity ratio is then of the order of 2,000, which seems to be strongly overestimated, especially since its irregular shape shows that it is strongly perturbed by the galactic tidal forces induced by the Milky Way. Unfortunately, this satellite, which is one of the smallest and weakest orbiting our galaxy, is approaching our Sun at a speed of 116 kilometers per second, or 70 miles per second. The Big Dipper 2 is inexorably subject to tides that cause strong disturbances over time, even irreversible dismantling. We could continue our journey through many such galaxies, including the Willman 1 galaxy, also located in the constellation of the Big Dipper, the Bouvier dwarf galaxy, the Berenice Hare dwarf galaxy, the Hercules dwarf galaxy, the Pisces 2 dwarf galaxy, or the Aquarius 2 dwarf galaxy. If all these galaxies have many points in common, I propose, however, that we linger with the Reticulum 2 galaxy, which is located in the southern constellation of Reticulum, halfway to the Magellanic Clouds. Its recent discovery dates back to 2015 and was only possible through the exploitation of data collected by the DES, Dark Energy Survey, which is an international optical and near-infrared survey research program. But Reticulum 2 did not reveal itself alone. It was spotted along with 8 other dwarf satellite galaxies orbiting the Milky Way. This discovery surprised astronomers who did not expect to find so many satellites in such a small area of the sky. Reticulum 2, which is probably spheroidal, is only 104,000 light-years away from our solar system, making it one of the closest Milky Way satellite galaxies. This object, called ultra-pale, like all the ultra-faint spheroidal dwarf galaxies we have just visited, contains very little observable matter. This small structure probably contains no more than 5,000 stars, themselves representing little more than 1% of the observable matter. Composed essentially of dark matter, which itself is only detectable by its gravitational attraction, this galaxy is 1 billion times darker than our galaxy and 1 million times less massive. If you observe it closely, you can see how it is being torn apart by the massive tidal forces it is undergoing as it comes into contact with the Milky Way. The discovery of these dwarf satellites in a handkerchief of pocket proves to be disconcerting and questions once again the scientists. Are they ancient satellites that orbited the Magellanic Clouds and were ejected by the interaction between the small and large Magellanic Clouds? Or were they originally part of a gigantic group of galaxies, destined, like the Magellanic Clouds, to be devoured by our own galaxy? What about you? What do you think? The vast majority of spheroidal dwarf galaxies occupy a position in space quite close to the 2 main members of the local group, namely the Milky Way and the Andromeda Galaxy, to which they are gravitationally bound. Most of them are gathered in a perimeter of only 7 million light-years. However, some dwarf spheroidal galaxies prefer to play solitary. These galaxies, which seem to have stepped out of line, are called isolated galaxies. What might an isolated galaxy look like? How does it behave in the universe? But above all, how did it form? This is what we will try to elucidate by getting closer to some of them. Let's start by visiting the Dwarf Whale Galaxy, which was long camouflaged in the constellation of the same name until its discovery in 1999 by a member of Cambridge University. It is respectively 2.46 million light-years away from the center of the Milky Way and 2.2 million light-years away from the center of the Andromeda Galaxy. Like its congeners, it has a low surface brightness. Its stellar mass is estimated at 2.6 million solar masses, while it appears to be devoid of hydrogen, so much so that this gas is not detectable. Its population of stars is relatively old. They would have been formed 12 billion years ago, during a short period of 2 to 3 billion years. It is therefore 8 billion years since no new stars appeared in the heart of this galaxy, which looks so peaceful. The effective radius of this galaxy is barely 2,300 light-years. Its radial velocity of 87 kilometers per second, or 55 miles per second, brings it slowly closer to our Sun, while its dispersion velocity is about 17 kilometers per second, or 10 miles per second. If you take a few moments to contemplate it, you will notice that it has a global rotation speed of about 8 kilometers per second, or 5 miles per second. This group of old, cold stars, like a ghost ship carried by weak cosmic currents, seems to wander in the universe like a lost soul. Another cluster of small stars, very faint and devoid of gas, was discovered in 1990 at the Mount Stromlo Observatory in Australia. This is the Toucan dwarf galaxy. Like the Whale dwarf galaxy, its surface brightness is relatively low, and its population of stars is comparable, most of them 13 billion years old. This tiny spheroidal galaxy is even smaller than the Whale, its effective radius being just over 926 light-years. It is about 2.8 million light-years away from our galaxy, and nearly 4.4 million light-years away from the Andromeda galaxy. But what makes it even more special is its position in the local group. If, like isolated galaxies of the same kind, it is at a certain distance from the two referent galactic monsters, on the other hand, it is located almost opposite most of the other members in relation to the Milky Way. Unlike many galaxies, it has a positive radial velocity, meaning that it is moving away from our Sun at a speed of 194 kilometers per second, or 120 miles per second, with a low velocity rotary motion, estimated at 16 kilometers per second, or 10 miles per second, in its outer regions. Among the isolated spheroidal dwarf galaxies, we can also mention KKR 25, located in the Dragon Galaxy. The latter was discovered in 1999 by three researchers who gave it their name, namely Karachentsev, and Richter. Like the two previous galaxies, it is characterized by its distance from the main members of the local group, estimated at more than 6 million light-years, but especially by its isolation from any other cosmic object. Another isolated galaxy attracts the scientific community, the KKS-3 galaxy. Difficult to spot because of its low luminosity, it is barely 7 million light-years away from the Milky Way. Its discretion is all the more important, as its total mass is about 20 million times that of the Sun. If it was detected in 2000, its isolation could be proven only in 2014 thanks to the Hubble telescope. The majority of the stars that compose it are old stars, formed probably 12 to 14 billion years ago. Devoid of gas since then, it has not created stars for a long time. It is therefore a relic that greatly interests astronomers because of its great age, but above all, because of its isolation. It has probably not undergone any change for a very long time, which makes it an ideal research laboratory to understand the cosmic workings and the foundations of the universe. The Hubble Space Telescope has been steadily revealing its findings since its launch in 1990. In 2018, it detected a galaxy that until then had gone unnoticed, as if forgotten, and for good reason. While scientists were observing the globular cluster NGC 6752, 13,000 light-years away from our solar system, in search of its faintest stars, a never-before-detected dwarf galaxy quietly appeared in the background, in the constellation Peacock, in the form of a very dense and elongated collection of faint stars. Distant by about 30 million light-years, the Bedin 1 galaxy was thus also the object of an accidental discovery. Hidden behind the bright stars of the cluster studied, this spheroidal dwarf, which places it in the category of isolated galaxies. It is even to date the most isolated galaxy of this type. Its closest neighbor is 2.12 million light-years away. NGC 6744, a large intermediate spiral galaxy, also located in the constellation Peacock. For the time being, It is not yet known whether these two galaxies are gravitationally bound, nor whether NGC 6744 is its host. But what makes Bedin 1 even more spectacular, apart from its isolation, is its age. Examination of its light spectrum, which is about 1,000 times smaller than that of the Milky Way, has led scientists to conclude that it has a very low concentration of metals. This galaxy, which was probably born during an explosion, has not experienced any new period of star formation since then. The stars in it are therefore very, very old. Bedin 1 seems to be one of the oldest galaxies ever discovered, and would be 13 billion years old. If you add 0.8 billion years to it, Bedin 1 would be as old as the universe. Considered by astronomers as a kind of living fossil of the primordial universe, having undergone no interaction with other cosmic monuments, it looks like a time capsule. Its preservation of the conditions of the primitive universe should still be able to give us many secrets concerning its creation. New generation telescopes, such as the W-FIRST telescope, should in the near future bring to light many other galaxies of this type, which have remained discrete for a long time because of their very low luminosity. As you can see, these objects have not finished to be talked about. I propose to you now to be interested in another category of galaxies. Let's discover some of the most beautiful irregular dwarf galaxies that embellish the local group with their colorful twinkling. Let's first discover the IC10 galaxy, located in the northern constellation of Cassiopeia, about 2.2 million light-years from our Sun. You immediately notice that it is much brighter than all the previous galaxies. Of course, it does not dazzle by its size, its diameter being about 5,000 light-years. No, it is by its different regions reflecting a reddish glow through intermediate dust clouds that it stands out. Unlike its fellow galaxies, the IC10 galaxy has a large population of newly formed massive stars. You are in front of the only starburst galaxy, i.e., a star-forming galaxy belonging to the local group. It contains more Wolf-Rayet stars, hot stars of several tens of solar masses, then the Magellanic Clouds, although much smaller. Observe its central part, where a large X-ray source can be detected. A high-mass X-ray binary is located there. It is composed of a Wolf-Rayet star and a compact object, which is none other than a stellar black hole, whose mass reaches several tens of solar masses. Look how these star formations punctuate the heart of this galaxy. Their production represents between 0.04 and 0.08 solar masses per year. The interstellar gas that feeds these numerous outbreaks can probably last for several billion years. What a magnificent sight! Now, look at the hydrogen envelope that surrounds this galaxy with its vaporous mantle. Look carefully. Its movement is different from that of the galaxy itself. Surprising, isn't it? Another isolated galaxy intrigues the astronomer's sphere. This is the Leo 3 galaxy, also named Leo A. As you have understood, it is located in the constellation of Leo. Distant from 2.25 million light-years from our Sun, it is also an irregular dwarf galaxy, whose mass probably does not exceed 800 solar masses. This gas-rich galaxy has a low stellar mass and low metallicity. Its largest diameter is about 6,500 light-years. It contains stars of different ages. The youngest are approximately 10 million years old, while the oldest are up to 10 billion years old. However, over 90% of its stars were formed less than 8 billion years ago. In total, it hosts 5 star clusters, 2 young low-mass clusters and 3 older ones, also low-mass. Despite these many stars, this galaxy is still 80% dark matter, which is still a mystery. You can admire its ancient halo of stars, which was discovered a few years later, in 2004. Take a closer look at this galaxy. Its internal ring structures remind you of the typical morphology of spiral galaxies. Its stars extend beyond its gaseous envelope. It thus resembles massive disk galaxies and proves that galaxies of very low stellar mass are just as capable of creating complex structures. Here is, once again, a galactic object that challenges the current understanding of galaxy evolution. Our journey is coming to an end. However, I would like to allow you to discover 2 last galaxies, which of course do not belong to the local group, but which are so close to it that we cannot be satisfied with observing them from far. It would be a shame to give up visiting them when we have never been so close to them, wouldn't it? Among the galaxies that populate the near periphery of the local group, I propose you to discover one of them, long considered wrongly as an irregular galaxy. Let's go to the constellation of the Sculptor, where we can admire the galaxy NGC 55, also named Cadwell 72. In the distance, it hides behind its flattened shape, making it look like a long, graceful comet with its disparate tails. In fact, it only lets us admire its narrow profile, extending over about 68,000 light-years. But look closely. As we get closer to it, we can change our angle of view. Isn't that wonderful? Look at this galactic object that is slowly being revealed. Doesn't it look strangely like the Large Magellanic Cloud? You can now contemplate this galaxy, which offers us a complete vision of its structure. In reality, Cadwell 72 is a barred spiral galaxy. Composed of a single arm, it falls more precisely in the category of Magellanic spiral galaxies. However, unlike the Magellanic Clouds, which are about 180,000 light-years away, this small galaxy is almost 7 million light-years away from our solar system. It is probably the closest galaxy to the local group known to date. Several 100 billion stars illuminate its flattened disk, but you can see how much denser and brighter its center appears. This is its bulge, characterized by this central and spherical bulge. This core, particularly bright, is crossed by clouds of dust. In some places you can observe iridescent colored areas. There are many regions of pink star formation, but also young clusters of blue stars, which testify to the activity that still reigns within this small galactic monster. Not far from there, another luminous object attracts our attention. Still in the constellation of the Sculptor, another spiral galaxy is next to the object, NGC 55. It is the galaxy NGC 300, or Caldwell 70. This one is also about 7 million light-years away from our Sun, is a low-surface brightness galaxy, its light being spread over a larger apparent area. If you look closely at its structure, you will see that it is not unlike our Milky Way. Its luminous halo, which extends over more than 55,000 light-years, is dotted with swarms of red giant stars that straddle its two spiral arms. Its bulb, too, has myriads of stars. Moreover, this galaxy has been the subject of many studies. It has even been portrayed. This feat is the result of 50 hours of exposure, spread over a number of nights of observation. The wide-field imager camera, which has a very large field of view comparable to that of the apparent surface of a full moon, was able to take a large number of pictures, which once processed with special filters and assembled, allowed the creation of a unique image. In addition to mapping this galaxy, which is comparable to our own in structure, it has revealed that it harbors a black hole of about 15 solar masses at its heart. This black hole belongs to a binary system and is close to a hot and luminous Wolf-Rayet star. Finally, only 1 million light-years seems to separate these two cosmic objects, namely NGC 55 and NGC 300. This galactic pair is most likely gravitationally bound. Do you think that one of these galaxies is destined to devour its sister? Or will they both be absorbed by an even more powerful galactic monster? We are approaching the nearest star system to our Sun. This is Proxima Centauri, a stellar and planetary system that also goes by the name of Alpha Centauri c. You'll understand why it's called Alpha Centauri in a moment. We are in the constellation of Centauri, only 4.2 light-years from Earth, and therefore still in our beautiful and luminous Milky Way. The luminous object you have before you is a red dwarf. These are very common in our galaxy. They represent nearly 80% of the stars in the Milky Way. The apparent magnitude of Proxima Centauri, which is equal to 11.05, does not place it in the category of the brightest stars, the most radiant stars being of first magnitude. In fact, 85% of the energy it emits is not visible to our eyes, being mainly in the infrared wavelengths. To the naked eye, its luminosity in visible light is almost 650 times less than that of our Sun. Proxima Centauri is therefore of spectral type M5, which explains why it was only discovered in 1915. With an actual diameter of 200,000 kilometers or 125,000 miles, it is 7 times smaller than the Sun, which is 1.5 times the size of Jupiter, the largest planet in our solar system. Its mass is about 12.3% of the Sun's. But Proxima Centauri has a medium density, and its density is much higher than that of the Sun. Unlike our star, which transmits its energy to the outside by radiation, Proxima Centauri transmits it by physical movements of the plasma. The interior of this star is therefore entirely convective. The helium which is produced by nuclear fusion, instead of accumulating in the center of the star, circulates inside it. This results in a convection phenomenon which generates a permanent magnetic field. This magnetic energy is extracted from the object in the form of stellar eruptions comparable to solar flares. Some of these explosions can reach incredible dimensions, corresponding to the size of the star itself, which considerably increases its total luminosity during a certain period of time. Nearly 80% of the star's surface is active, which is far beyond the activity that we know of the Sun. This is why the temperature of its corona, even outside its peaks of activity, remains higher than that of the Sun. It reaches 3.5 million degrees Celsius, or 6.3 million degrees Fahrenheit, while our Sun does not exceed 2 million degrees Celsius, or 3.6 million degrees Fahrenheit. This violent activity is nevertheless less important than many other red dwarfs can undergo, probably because of the advanced age of this star, which is estimated at several billion years. Proxima Centauri is a planetary system. The star does not evolve alone, far from it. It is accompanied by not one, but 3 planets orbiting it. The first, Proxima Centauri b, is a telluric planet located in the habitable zone of its host, at a distance of 7 million kilometers. Its orbital period is just over 11 Earth days. Its mass, about 1.3 times that of our Earth, and its equilibrium temperature suggest that there could be water in a liquid state on its surface. But if we assume that this exoplanet has no atmosphere, which has been destroyed by repeated stellar eruptions, no form of life could be found there. The proximity of the two objects probably leads to a synchronous rotation, which means that this planet permanently shows the same face to its star. As a result, Proxima Centauri b could experience very high temperatures on its exposed side, hindering the presence of liquid water, while its hidden side would be extremely cold, covered mostly by ice. But what about the regions located between these two zones? Do you believe, in case of the presence of an atmosphere, that a life is possible at the level of the Terminator, this border connecting the two faces? The second planet that orbits Proxima Centauri is a cold super-Earth of the mini-Neptune type. This is Proxima Centauri c. With a mass of 5.8 times that of the Earth, it is located at about 1.5 astronomical units from its star. Its orbital period is 1900 days, or a little more than 5 Earth years. Finally, an exoplanet, whose mass is a quarter of that of the Earth, was detached in 2022. It is Proxima Centauri d, an exoplanet distant from its host by only 4 million kilometers or 2.5 million miles. Life on this planet, which orbits in only 5 days, is fatally impossible because of its proximity to the star. Furthermore, Proxima Centauri, although discovered late, was found to belong to an even larger system. In fact, it is only the third and smallest star in a triple system, Alpha Centauri, which has been known for much longer. Do you see, not far from there, these two stars which make you eye? I suggest that we get closer to these two bright stars, Alpha Centauri A and Alpha Centauri b, which form the main duo in this triple system. They are distant from their third companion by nearly 13,000 astronomical units, or 1,950 billion kilometers, or 1,200 billion miles. This distance, which is only 5% of the distance between Alpha Centauri AB and our Sun, still suggests an orbital period of Proxima Centauri between 507,000 and 613,000 years around the main duo. The distance and its low orbital velocity explain why Proxima Centauri has long been excluded from this system, to which it is nevertheless gravitationally bound. To the naked eye, this binary system, because of the proximity of its components, appears from our Earth as the brightest star in the constellation Centauri, and the third brightest in our sky, with Sirius and Canopus surpassing it. Similar to the Sun, the two stars that compose it are respectively of class G2 and K1. Alpha Centauri A, also named Rigil Cantaris, is the largest of the stellar duo, with a mass equivalent to 1.1 solar masses and a luminosity 1.519 times that of the Sun. It is a yellow dwarf that is 10% more massive than the Sun, with a radius 22% larger. In short, you are looking at the twin sister of our Sun. Alpha Centauri B, also called Ptolemy, is slightly smaller and cooler than its companion. The mass of this secondary star is 90% of that of the Sun, and its diameter only 14%. Its luminosity is barely 45% of that of the Sun. Therefore, it has a main sequence of spectral type K, which gives it this more orange color. These two stars orbit each other in 80 years. Their orbits, slightly eccentric, bring them closer to each other by 11.2 astronomical units, or about 1.68 billion kilometers, which is the distance between the Sun and Saturn. When they move away, they can be up to 35.6 astronomical units, or 5.33 billion kilometers, or 3.1 billion miles, which is equivalent to the distance between Pluto and our Sun. Astronomy enthusiasts will have to wait until May 2035 to benefit from the next Paracenter in order to observe this pair in optimal conditions. Their orbital period will then have brought them closer. But our interstellar journey gives you today the possibility to observe them as never before. So let's take advantage of it to know a little more. Do you think that this star system, which is home to stars resembling our Sun, could harbor any form of life? And why wouldn't there be, in this not-so-distant land, some hot and rocky planets with a lot of water, comparable to our Earth? If you look at the near environment of Alpha Centauri A, at first sight, no planet is visible. However, a candidate exoplanet named Candidate 1 has been studied by astronomers since 2021. Distant of about 1.1 astronomical units from the star, with a revolution estimated at 1 year, it could in fact be only a dust disk, or even an artifact. On the other hand, Alpha Centauri B could have several companions, even if they have not been confirmed by the scientific community. The first, detected in 2012, would be a planet whose mass, greater than 1.1 and 2.7 times that of the Earth, qualifies it as a super-Earth. It is called Alpha Centauri BB, or Gliese 559BB. Only this candidate orbits in a non-habitable zone with respect to its host star on a short period of 3.24 days. Distant from 0.04 astronomical units, or only 6 million kilometers, or 3.7 million miles from its star, you can imagine that no life can develop there. The very high temperatures of this planet would be able to melt lead, but recent studies have shown that Alpha Centauri BB is actually a statistical ghost. It has therefore disappeared from the list of exoplanets. The second companion, Alpha Centauri BC, is another candidate planet that seems to evolve little further than the previous one, with an orbital period of less than 20 days. Its size, 92% that of the Earth, would have made it an ideal telluric planet. But once again, its proximity to the star that hosts it makes the presence of water in a liquid state on its surface impossible. At present, it is finally near the smallest star of this triple system, Proxima Centauri, that we are most likely to discover a habitable planet, at least in part. But let's see what the next solar systems can tell us. Although more distant, they could hold some nice surprises. Let's start with Barnard's Star, which is located a little further away, in the constellation of Ophiuchus, 5.9 light-years from our Sun. Despite its proximity to our solar system, its low luminosity prevents its observation without a telescope. Indeed, it is a red dwarf of spectral type M4. In other words, it is an old lady. Of an advanced age of some 10 billion years, it presents a deficiency in metal. It contains barely 25% of the amount contained by the Sun. Moreover, it has lost a lot of its rotation energy. This one is 130 days, which is relatively slow compared to the one of the Sun, which makes it in 25 days only. Much less radiant than our Sun, it is hardly more luminous than 100 full moons cumulated. Its mass represents 17% of solar mass, and its radius 15 to 20% of the Sun's. However, this star monopolizes the sphere of scientists for various reasons. Under its calm airs, it can still show strong fits of anger, resulting in significant stellar activity. Moreover, in 1998, an intense stellar flare was observed. The temperature reached during this eruption exceeded 7,700 degrees Celsius, or 13,800 degrees Fahrenheit, more than double the temperature of the star. Barnard's Star is therefore a so-called eruptive star. In addition, it is sometimes called the runaway star of Barnard. If the stars appear as fixed points in our night sky, they all move in our universe. But these movements, when compared to the scale of our human lifetimes, seem insignificant. However, Barnard's Star holds a speed record. It is the fastest moving star in our Earth's sky, not following the general flow of stars around our Milky Way. To give you an idea, this star moves across our sky about one full moon width over a period of 174 years. This may seem extremely slow to you, but compared to other stars, Barnard's Star feels like it is spinning through the sky, with a relative lateral speed, that is, sideways to our Sun, of 90 kilometers per second, or 55 miles per second. Its radial velocity brings it closer to our solar system at the crazy speed of 140 kilometers per second, or 85 miles per second. By the year 11,800 AD, Barnard's Star should be only 3.8 light-years away from our Earth. You are probably wondering why we are visiting Barnard's Star. Why are we interested in this isolated star that doesn't seem to belong to a system? In fact, Barnard's Star is a small planetary system. This star, which has monopolized planet hunters for several decades, has been the subject of more than 770 observations. Astronomers saw their efforts rewarded in 2018. An exoplanet does orbit near Barnard's Star. It is Barnard's Star B, also known as the planet Barnard B. This rocky planet has a mass equivalent to 3.2 times that of Earth, making it a super-Earth. Distant from about 60 million kilometers or 37 million miles, twice as close to its host as the Earth is to the Sun, it revolves in 233 days. But this close distance is not enough to place it in the habitable zone of this red dwarf. The exoplanet Barnard B, compared to our Earth, receives only 2% of the energy of its star. It evolves just beyond what is called the ice line. Its surface temperature is so cold, approximately minus 170 degrees Celsius or minus 274 degrees Fahrenheit, that the presence of liquid water is highly unlikely. This planet cannot support any form of life. Too bad. This discovery, which is the result of an important collaboration between many scientists from all over the world, follows 20 years of studies performed with 7 different instruments. However, other candidate planets are being studied in this stellar region, including Barnard Star C and Barnard Star D. But so far no study has been able to confirm their presence. Astronomers now know that they are likely to discover many other planets of this type near red dwarfs, especially as technologies continue to progress. The only thing left to do now is to find an exoplanet that has the right conditions to support life. Let's continue our interstellar journey and reach the binary system Lumen 16, which is only 6.5 light-years away from our Sun. Composed of 2 brown dwarfs, it is located in the southern constellation of the Sails. To date, it is the closest known pair of brown dwarfs to our solar system. Their recent discovery, which dates back only to 2013, was the result of a 13-month mission by NASA's WISE spacecraft. It acquired about 1.8 million images of asteroids, stars, and galaxies. But first, what is a brown dwarf? In reality, it is an object too massive to be considered a gas giant, but not massive enough to be a star, being unable to trigger nuclear fusion at its center. Brown dwarfs are sometimes compared to failed stars. The main component of this binary system is of spectral type L8. The second, even less bright, is also a late bloomer that appears closer to the transition threshold. These 2 objects, which are separated by more than 3 astronomical units, orbit each other in about 25 years. This slowness is explained by their low mass, although it represents about 30 times that of Jupiter. Like Jupiter, the 2 brown dwarfs are subject to strong winds, as evidenced by the bright stripes running parallel to their respective equators. If you take a closer look at Object B, you will see a complex structure of irregular clouds on its surface, sometimes light, sometimes dark. Composed of iron droplets and other minerals, these disparate clouds present extreme weather conditions, with temperatures exceeding 1,000 degrees Celsius or 1,832 degrees Fahrenheit. But let's be careful and keep our distance from this molten iron rain. Because of their low luminosity, these 2 red dwarfs offer scientists an open-air laboratory that should allow them to study this type of object more easily. Brown dwarfs could reveal the secrets that govern planetary evolution, but also the formation of stars. They could even allow the discovery of exoplanets. While brown dwarfs are not massive enough to allow hydrogen fusion like stars do, they do cool slowly as they contract and their surface gravity increases. As a result, the surface temperature of a brown dwarf can vary considerably. It can reach degrees almost comparable to those of a star, and on the contrary, degrees as low as those of a cold planet. Their age and their physical composition are as many parameters that make them different from each other. They can then present great diversity of colors and spectral characteristics. Slight perturbations are observable in the orbits of these two brown dwarfs. A planet is probably at the origin of these variations. But to find this unconfirmed object, we must know on which side to look, and at what distance. Because as we have already seen, even at very large distances from each other, objects can be linked. Let's go now to the constellation of Hydra to discover the star Y0855-0714. This star is 7.2 light-years away from our Sun. This short distance on the cosmic scale makes it the fourth closest star to our Sun. Its physical characteristics place it in the category of sub-brown dwarfs, or brown dwarfs of planetary mass, its mass corresponding to 1% of the solar mass. Its formation, identical to that of stars or brown dwarfs, is the result of the collapse of a gas cloud. Only its mass, which is 10 masses of Jupiter, remains lower than the 13 masses allowing it to generate the thermonuclear fusion of deuterium, so that it can claim the status of star. If this type of object is often classified in the category of brown dwarfs of planetary mass, some scientists consider them as planets floating freely in the cosmos. Y0855-0714 is even cataloged by some as a rogue planet, especially since it seems to evolve alone, without any companion at its side. Its discovery, made possible by WISE, NASA's Wide Field Infrared Explorer, dates back to 2014. This star, whose radius is slightly smaller than Jupiter's, has average temperatures worthy of the North Pole, from about -48 degrees Celsius to -13 degrees Celsius, or between -54 degrees Fahrenheit and 9 degrees Fahrenheit. Colder than Earth's average temperatures, but warmer than those on the surface of Jupiter. Therefore, among all its fellows in interstellar space, it is the coldest object of all. But this is not what surprised astronomers the most when they observed it. Let's get a little closer to this failing star. Its spectral type Y allows us to observe its surface more closely, without the need to protect our eyes. We can admire in an atmosphere tinted with azure shades, clouds similar to those surrounding our beautiful blue planet. Isn't it extraordinary? These clouds are composed of water ice crystals and sodium sulfide. This is a first for scientists. If water vapor has already been detected in the atmospheres of exoplanets, this is the first time that water clouds are observed outside our solar system. Even at the closest to our planet, these observations are generally only possible on Earth or Mars. The giant planets are so cold that the ammonia ice clouds mask the water clouds, as on Jupiter and Saturn, and the atmospheres of Neptune and Uranus prevent any visibility. All in all, this so-called failing star is of great interest to the scientific community, especially since it evolves alone in interstellar space. As you have probably noticed, no other object seems to be gravitationally linked to this failed star. Observations looking at it therefore cannot be subject to interference from a nearby star that could cause any glare. Let's now turn our attention to another star system, also located a short distance from our solar system. Let's go to the constellation Leo, where a red dwarf has, like our Sun, a corona. Here we are approaching Wolf 359, a star that is certainly quite pale, with a spectral type of class M6.5, but which hosts two exoplanets. They are respectively named Wolf 359b and Wolf 359c. Wolf 359 is one of the smallest stars known to date, its mass of 0.09 solar masses being at the lower limit. Indeed, a star whose mass is lower than 0.08 solar mass is not massive enough to ignite the hydrogen of its core. Wolf 359 is then at the limit to be considered also as a brown dwarf. Because of its small size, its radius being only 0.16 solar radius, it is entirely convective. The helium produced in its center arrives at its surface thanks to the movement of the plasma. Because of this weak and slow production of energy, it will probably remain in this state much longer than our Sun, which burns its cartridges at high speed. The life of the latter is estimated at 10 billion years, and we know that it has reached 4.55 billion years. In place of our Sun, the faintness of Wolf 359 would represent about 10 times the brightness of our full moon. Not enough to cause us the slightest sunburn, even worse, not enough to hope for any presence of life on our planet, which would then be covered with ice. However, this young spinner, at least 100 million years old, and whose projected rotation speed is less than 3 kilometers per second, or 2 miles per second, is a flare star. In other words, a variable star. Of UV Ceti type, it undergoes sometimes brutal increases of its luminosity on all its spectrum. Its magnetic activity induces brief eruptions which can occur at a rate of 32 events over a period of 2 hours, most of them being microeruptions. Its surface temperature, much lower than that of our Sun, is nevertheless 2,500 degrees Celsius, or 4,532 degrees Fahrenheit. This temperature is low enough for the chemical compounds to remain long enough to be observed with their spectral lines. In 2001, molecular lines composed of carbon monoxide, iron hydride, chromium hydride, water, magnesium hydride, vanadium oxide, or titanium oxide could be observed for the first time from a terrestrial telescope. Apart from the Sun, Wolf 359 is therefore the first star to expose the spectrum of its corona to the light. The study of its spectrum revealed the absence of lithium lines. This element has probably been entirely consumed by fusion in the core. This is the parameter that allows us to conclude that this star must be at least 100 million years old. As we have seen, Wolf 359 is not alone. It has two companions. 2 planets orbit around it. The first, Wolf 359b, is 276 million kilometers, or 170 million miles away, and the second, Wolf 359c, is close to 2.7 million kilometers, or 1.7 million miles. The more distant of the two has a mass of about 43.9 Earth masses and orbits Wolf 359 over a period of 2,938 days. The closer one, Wolf 359c, is much less massive, with its 3.8 Earth masses. It orbits its star in 2.7 days. Unfortunately, these 2 planets are either too far away or too close to their host to be located in the habitable zone, which extends from 3.6 and 7.7 million kilometers away, or between 2.2 and 4.7 million miles. Wolf 359b would be so cold that it could only be covered by a thick coat of ice, while its companion, Wolf 359c, would suffer from temperatures too high for water to remain in liquid state on its surface. Our efforts to find a potentially habitable exoplanet will therefore have to focus on another star system. Another red dwarf located in the Big Dipper constellation and 8.3 light-years away from our Sun is particularly promising. Let's join the second Argelander star, better known as Gliese 411 or Lalande 21185, an old lady between 5 and 10 billion years old. This red dwarf of type MV5 is cold and dark. Its luminosity, which is 6,000 times lower than that of our Sun, does not prevent it, however, from being among the brightest red dwarfs in the solar neighborhood. Its apparent magnitude is only 7.47, so it cannot be observed with the naked eye. It has all the characteristics of a half-sun, a mass of about 46% of solar mass, and a diameter equivalent to 40% of that of the Sun. If its mass had reached 50% of solar mass, it would probably have entered the category of red giants. Its surface temperature, which is about 3,328 degrees Celsius, or 6,022 degrees Fahrenheit, or 62% of that of the Sun, can undergo sudden variations as well as its luminosity. Indeed, Gliese 411 is a so-called eruptive star, a flare. The eruptions on its surface are as unpredictable as they are spectacular, especially since the excess luminosity produced contrasts with the usual pallor of the star. At first sight, apart from its spectral anger, this star has nothing extraordinary. However, it integrates the list of interesting objects for exoplanet hunters. On the one hand, because of its proximity to our Earth, and on the other hand, because of its constant radial velocity. It is a perfect example of the stability level of red dwarfs, although it moves perpendicular to the galactic plane at high speed with an average of 47 kilometers per second, or 30 miles per second. In its interstellar course, Gliese 411 undergoes, however, astrometric perturbations. The study of these variations has established that this red dwarf is indeed part of a multiple system. Since 1996, it is known that not one, but 2, or even potentially 3 planets are in orbit around Gliese 411, which is therefore the 4th closest planetary system to our Sun, after Alpha Centauri, Barnard's star, and Wolf 359. The first planet is called Gliese 411b. It is a super-Earth. Its mass corresponds to 3 Earth masses. Very close to its star, at 0.08 times the distance Earth to Sun, it completes its orbital period, which is very circular, in only 13 days. Gliese 411b is 5 times closer to its host than Mercury is to the Sun, and although this star is less hot than the Sun, the planet is not in the habitable zone. It receives 3.5 times more energy than the Earth receives from the Sun, and must therefore have strong similarities with Venus. A second planet evolves at a little less than 3 astronomical units from the mother star. This is Gliese 411c. This exoplanet, whose mass exceeds 13 terrestrial masses, covers its orbit in 2,946 days. It is therefore a Neptune-like planet, located well beyond the habitable zone. Finally, a third planet could also interfere with the main star, placing it in the category of quadruple systems. Named Gliese 411d, it is 0.5 astronomical units away from its host. With a mass equivalent to 4 Earth masses, it has an orbital period of 215 days. It remains to be seen if its temperature and atmosphere are suitable or not for any form of life. What about you? What do you think about it? But let's leave this question aside for the moment. A star, sparkling like no other, attracts your attention, and for good reason. You are looking at Sirius, the brightest star after the Sun in our winter sky. You know, the one that flashes in the sky, reminding you of the intermittent lights of a plane at high altitude. Moreover, its name, which was not chosen at random, means bright in Greek. We find traces of its sparkling presence since the dawn of time. For the ancient Egyptians, the Nile star, as they called it, announced the periods of flooding of the river. In Chinese astronomy, it was called the celestial wolf, while the Greeks associated it with the dog of Orion, then called Sirius. This star also played a fundamental role for Polynesian navigators by serving as a landmark. The stars were their only reliable tool for orientation at sea, and Sirius, easily recognizable, marked the zenith of the most honored place of worship in the entire Polynesian region. It is located in the constellation of the Great Dog at a distance of 8.6 light-years from our own system. That is why it is also known as Alpha Canis Majoris, being the brightest star in this constellation. Its apparent magnitude is -1.46. To be clear, this negative number means that Sirius is brighter than our Sun, a magnitude of 1 being equivalent to the solar luminosity. This is why, despite a distant, but at the same time so close to our solar system on the scale of the cosmos, Sirius, which is classified in the category of white stars, appears so bright. Its brightness is punctuated by variation when observed from Earth. As you can see, however, it does not blink any more than our Sun. This effect is due to the fact that Sirius is located very low on our Earth's horizon. The light emitted by the star must therefore cross a large part of the atmosphere before reaching us. It is therefore more or less masked by the turbulence of the environment that separates us from it, hence its flickering. During our approach, if you look carefully at Sirius, you see that it is in fact a binary star. It is composed of 2 stars. The main one, Sirius A, is a white, slightly bluish star of spectral type A0 or A1. More luminous than our own star, it is 2.3 times more massive and 1.8 times larger than our Sun. I let you imagine the heat that reigns on its surface, its temperature being higher than 9,600 degrees Celsius, or 17,300 degrees Fahrenheit. That is to say, much more than our Sun, which burns at 5,504 degrees Celsius, or 9,930 degrees Fahrenheit. All these characteristics evoke the relatively young age of Sirius, which should not have more than 200, even 250 million years. It has for companion a white dwarf named Sirius B. The latter, because of its small size, its proximity to Sirius A, and its low magnitude of only 8, was discovered only very late in 1862. As a white dwarf, Sirius B has a size comparable to that of the Earth, while its mass is equivalent to that of the Sun, and its estimated temperatures are 3 times higher than those of Sirius A. Separated from the main star by an average of 19.5 astronomical units, or 19.5 times the distance between the Earth and the Sun, it orbits around it over a period of 50 years. Because of a strongly marked elliptical orbit, the distance between these two stars can vary from 8.1 to 31.5 astronomical units. This maximum distance will soon be reached by 2024 to 2025, while the next passage at the periastron of the system, i.e. the moment when the two stars will be the closest, is planned for 2044. This binary system is waving alone in the cosmos. No planet has yet been seen in its vicinity. Sirius being a young star, it is unlikely that exoplanets are in orbit around it. However, since 2018, NASA has been exploring this bright object with the Transiting Exoplanet Survey satellite. And who knows, its high brightness could mask one or even several planetary objects. At almost the same distance from our Sun, another stellar duo awaits us. Let's join, at 8.7 light-years from our solar system, Luyten 726-8, a binary system hosting two stars, BL Ceti and UV Ceti. They are once again two M-type red dwarfs, probably younger than our solar system. With a low luminosity, they are not visible to the naked eye. This is why they were only discovered in 1948. These two stars, like twin sisters, have many similarities. Both have almost identical masses, radii, and luminosities. Their mass is 10% of the solar mass, their radius 14%, and their combined luminosity is 11,000 times less than that of the Sun. It is therefore not surprising that we detect an identical temperature on the surface of these two stars, which is close to 2,330 degrees Celsius, or 4,220 degrees Fahrenheit. If the two stars orbit around a common barycenter over a period of 26.5 years, their orbits are marked by a strong eccentricity. The distance between them can therefore vary between 2.1 and 8.8 astronomical units, causing strong tidal forces between the two objects. BL Ceti, the main component of this duo, has a luminosity 6,000 times lower than the Sun, while the secondary star, UV Ceti, has a luminosity 4,000 times lower. UV Ceti is the better known of the two. The latter rotates very fast, with a rotation of only 0.2 days. Its rotation speed feeds a powerful magnetic field, where bubbles, charged with matter by the convection currents typical of red dwarfs, trigger important eruptions. UV Ceti is therefore a flaming star. During one of its numerous eruptions, its luminosity can be multiplied by 100 in a few seconds. At the same time, massive emissions of UV and X-rays ignite the star's environment. In 1952, the observation of UV Ceti allowed to count not less than 75 variations of its luminosity in only 20 seconds. This particularity places it in the category of variable stars, where, moreover, it serves as a reference. Indeed, other eruptive stars are sometimes included in the category of UV Ceti variables. The main star is less active. This is probably related to the fact that it has a lower rotation speed. Nevertheless, the motions of these two stars are at the origin of unusual stellar winds. Their surfaces are subjected to winds more violent than those experienced by the Sun, although weaker at equivalent distances. The resulting heliosphere extends to 10 or 20 astronomical units. During massive eruptions, this heliosphere can be expelled up to 100 astronomical units. When the eruption of one of the two stars is directed towards the second, a shock zone is created, somewhere between the two stars, giving a complex and non-spherical shape to the heliosphere surrounding UV Ceti. In short, the environment near this star system does not seem to be the most favorable to host a planet in the best conditions. This one, in addition to being subjected to stellar winds, would inexorably undergo the unpredictable explosions of anger of UV Ceti. However, oscillations have been noticed in the orbits of the two stars, in particular that of BL Ceti. But what could a planet located in this tiny part of space look like? A hypothetical planet orbiting UV Ceti would have no atmosphere, as it would be deteriorated in a few millennia by repeated flares. On the other hand, a planet orbiting BL Ceti could keep its atmosphere for more than 100,000 years. However, the important forces of tide undergone would dress this planet of a multitude of volcanoes, where the only existing rivers would welcome only the flows of a burning lava. Moreover, the strong fluctuations of temperatures would have reason of the rock present on its surface, transforming it gradually into dust, which would mix with the volcanic ashes. A planet in orbit around these two stars would be more than 30 astronomical units away. Of course, it could contain its atmosphere, but its temperatures below -230 degrees Celsius or -382 degrees Fahrenheit would not be very attractive, and the luminosity on this planet would be null, except during strong stellar eruptions. In short, if the binary system Luyten 726-8 can be attractive by its spectacular side, it is not very welcoming. Ross 154 is the 9th closest star system to our Sun. Located in the constellation of Sagittarius, it is 9.7 light-years away. Composed of a main sequence star of spectral class M3.5V, it is not visible to the naked eye from our Earth. Ross 154 is therefore by definition a red dwarf star, cold and dark. Its discovery by Frank Elmore Ross dates back to 1925. Ross 154, also named Gliese 729, has a mass equivalent to 17% of solar mass. Its size is about 20% of the Sun. Its apparent magnitude is only 10.44. The luminosity of this star is relatively low and represents only 0.4% of the Sun. Ross 154 is so small that it is not able to expel heat from the core at its surface, as do the larger red dwarfs. So it carries this heat to its surface by convection. Moreover, as you can imagine, the heat at its surface is much lower than that of our Sun. It is estimated at 3,019 degrees Celsius, or 5,460 degrees Fahrenheit. However, this star is not so ordinary. Like many red dwarfs, it is an eruptive star. Moreover, it integrates the category of UV Ceti-type variables. This flare star, during prodigious eruptions, can thus generate X-ray emissions comparable to, or even superior to, those of the Sun. In addition, to integrate the catalog of eruptive stars, Ross 154 is also part of the variable stars of type BY Draconis because of its variations of 0.03 magnitude, noted on a period of 2.87 days. In addition, its relatively low metallicity, estimated at 56% of that of the Sun, as well as its moderately high rotation speed of 3.5 kilometers per second, or 4 miles per second, allow to conclude that it is a relatively young star. Ross 154 is less than 1 billion years old. No planet has been detected in its environment. In any case, as for a large part of red dwarf stars, the numerous and violent eruptions which burst out at its surface would fatally harm any form of life which could develop in its habitable zone, the planet having necessarily to be close to the star. In the constellation of Andromeda, another red dwarf has almost the same characteristics. It is Ross 248, also known as Gliese 905. Located at 10.3 light-years from our solar system, it is similarly a flaming star that sometimes increases its brightness suddenly. Its mass is about 12% of the solar mass, its diameter is 7%, and its luminosity is 11,000 times lower than the Sun's. Periods of variability have been reported, ranging from 4.2 years to 120 days, and 5 others between 60 and 291 days. What if these were astrometric disturbances that could be attributed to the presence of an invisible companion? For the moment, no planet or other object has been found orbiting this star. In any case, the meteorological vagaries of this star can only harm any form of life in its proximal periphery, if it could have developed at all, especially since its reddish color would prevent any form of terrestrial-type plant life from properly carrying out its photosynthesis process. Another star system is of great interest to the scientific community. It is an orange dwarf star that plays hide-and-seek. Let's go to discover this mysterious star in the constellation of Eridanus, 10.5 light-years from our solar system. This is Epsilon Eridani, also known as RAN. Its apparent magnitude of 3.73 makes it the third closest individual star system visible to the naked eye. Younger than our Sun, it is between 200 and 800 million years old. Being a main sequence star of spectral class K2, the energy generated in its entrails by the nuclear fusion of hydrogen is diffused at its surface, where the temperature is higher than 4,800 degrees Celsius, or 8,670 degrees Fahrenheit. This is what gives it its beautiful orange color. Slightly smaller than our Sun, its mass is 82% of the solar mass, and its radius is 74% of the Sun's. Its average period of rotation is 11.2 days. Epsilon Eridani is thus more than twice less fast than the Sun. If its luminosity is only equivalent to 34% of the Sun's, on the other hand, it generates a level of magnetic activity higher than that of the Sun. The chromosphere and the corona that surround it are therefore much more dynamic. As a proof, the average intensity of the magnetic field at its surface is 40 times higher than that of the Sun, and its stellar winds 30 times more violent. But this activity is not regular at its surface. Some regions are much more active than others. Epsilon Eridani is therefore considered as a variable, BY Draconis. It is a star that has a disconcerting behavior. Sometimes it brightens, sometimes it darkens. It has cycles of 27 years during which its brightness decreases considerably over a period of about 2 years. This decrease in intensity was last seen from 2009 to 2011. What gigantic object could shadow this star so much? It is known that Epsilon is surrounded by not one, but 2 rocky asteroid belts. One, 3 astronomical units away from the star, the second, 20 astronomical units away. However, they cannot explain this particularity. In fact, Epsilon is a binary star with eclipses. This means that it is accompanied by a dark object, probably a star, or even a pair of stars, surrounded by a disk of dust, dense and thick enough to make it invisible. These 2 stars are probably 30 astronomical units apart, and the diameter of the ring surrounding this pseudo-dark star must reach 20 astronomical units, occulting the main component like a curtain. However, Epsilon still reserves us a surprise. In addition to these variations of light, a study over 20 years of its radial speed has highlighted periodic variations. This observation has allowed to highlight the presence of a giant planet of the size of Jupiter in orbit around the star. This planet, named Epsilon Eridani b, or AE-Jur, follows a slightly eccentric elliptical orbit. Its semi-major axis is equivalent to the distance between our Sun and the asteroid belt. The size of this gas giant is estimated between 80 and 160% of the size of Jupiter. It completes its orbit in 7 years. If a planet could have formed in this environment, it is probably not alone, especially since the observed dust cloud has an asymmetry that could be explained by the presence of a second planet. This one would then be located much further away than the first one and would have a much longer orbital period. I now propose you to join another red dwarf. Yes, another one. Remember, red dwarfs alone account for about 80 to 85% of the stellar population in our galaxy. But this star should be of great interest to you, as it is considered by the scientific community as the best star to search for potentially habitable exoplanets. Let's discover Gliese 887, also known as Lacaille 9352. It takes the 12th place in the list of stellar systems closest to the Sun. Located in the constellation of Southern Pisces, 10.7 light-years from our Earth, it appears to be the brightest red dwarf in our sky and requires only a small telescope to be observed. Its luminosity is about 1% of that of the Sun. It is also the most massive of all red dwarfs, with nearly half a solar mass, at a distance of 6 parsecs from the Sun, or a little less than 20 light-years. But what makes this star even more exceptional is its low photometric variability, which makes it a quiet red dwarf like no other. Unlike its companions, Gliese 887 is less magnetically active and does not seem to ignite by triggering huge explosions or stellar eruptions. In other words, if there are planets orbiting in its narrow habitable zone, we could well detect traces of life there, and even, why not, consider terraforming them when technology allows it. This is very good news. On the one hand, the inactivity of this star greatly facilitates the remote observation of any exoplanetary atmosphere. On the other hand, exoplanets orbiting Gliese 887, which have not undergone many energetic explosions, may have retained their original atmosphere. What if I were to reveal to you that at least 2 exoplanets have been identified near this star? The first, Gliese 887b, is a super-Earth of about 4 Earth masses. It orbits its star in 9.3 days. Unfortunately, the small distance between it and its host, a little over 10 million kilometers, or 6.2 million miles, means that the temperature is far too high for water to be present in a liquid state. The second, Gliese 887c, is also a super-Earth, whose mass is estimated at 7 times that of the Earth. It orbits the star in 21.8 days. Do not rejoice too quickly, because unfortunately, for it too, the conditions are not optimal for it to harbor any form of life. Although a little further away from the star than the first described super-Earth, it is only 17 million kilometers or 11 million miles away. Once again, it is too close, and therefore too hot to maintain water in a liquid state, the temperature of its atmosphere having to reach at least 70 degrees Celsius, or 158 degrees Fahrenheit. However, any hope of finding an exoplanet in the habitable zone of Gliese 887 is not abandoned. Moreover, a candidate planet has been located in the habitable zone of this planetary system. Named Gliese 887d, this super-Earth of 8 Earth masses orbits its star in 50 days. Contrary to the 2 previous planets, it could therefore experience temperate temperatures and could therefore be well suited to the development of life. Another planetary system, also a little less than 11 light-years away, is located in the zodiacal constellation of Virgo. Let us now approach Ross 128, also named Gliese 447, the 13th closest star system to our Sun. This star has an apparent magnitude of 11.13. Its luminosity is therefore 100 times too low to be observed with the naked eye from our Earth. The primary object of the system is once again a red dwarf. Its mass is 15% of the solar mass, and its radius 21% of the Sun's. The temperature of its stellar atmosphere is 2,900 degrees Celsius, or 5,252 degrees Fahrenheit. Most of the energy radiated by the star is visible only in the infrared, with a luminosity 33,000 times lower than that of the Sun. As a result, it is of spectral type M4V, hence its typical cold orange-red color. Twice as old as our Sun, this star has been shining for over 9.4 billion years. Despite an entirely convective activity and a rotation speed considered slow, this flare star seems to have a long-term stellar activity cycle. As mentioned earlier, Ross 128 is part of a system. It hosts an exoplanet. This one, probably telluric, orbits in the interior edge of the zone of habitability, and thus receives approximately 38% more sunlight than the Earth. The planet Ross 128b is therefore potentially habitable. It is, after Proxima Centauri b, the second closest exoplanet to our solar system to enter this coveted category of cosmic objects. Let's see what this satellite looks like. Slightly more massive than Proxima Centauri b, Ross 128b contains at least 1.35 times the mass of the Earth. According to its hypothetical composition, if it is composed only of pure iron, it could have a diameter equivalent to half that of our Earth. According to the opposite hypothesis, if it is only composed of hydrogen and helium, it could then measure 3 times the size of the Earth. But considering that this planet could be telluric, its radius could be 1.1 times the Earth's radius, or about 7,000 kilometers or 4,350 miles, and its mass would then be 35% more massive than that of the Earth. Depending on its atmospheric component, its surface temperature could even be approximately the same as that of our Earth. Assuming that all these parameters are green, what about those related to the orbit of this planet? Ross 128b orbits rapidly around its star, in only 9.9 Earth days. This orbit is quite circular, thus having an eccentricity of only 0.036. It is more than 20 times closer to its host than the Earth is to the Sun, at a distance of 7.4 million kilometers, or 4.6 million miles. This proximity suggests that the planet has a gravity barely greater than that which we experience on Earth. But above all, it must always present the same face to its host. Apart from this particularity, this exoplanet is the only one known to date to resemble so closely our beautiful blue planet. But we must not lose sight of the fact that red dwarfs can be angry. Although the Olympian calm star Ross 128 seems to behave peacefully, it could have eroded the atmosphere surrounding the planet, evolving next to it in the past, during massive and repeated eruptions. But if this is not the case, if this star has always been peaceful, then Ross 128b could well be enveloped by an atmosphere. Why not? Welcome it. We could even go so far as to consider that it could already be home to one or more extraterrestrial life forms. Our interstellar journey is coming to an end. It has taken you almost 11 light-years from our Sun. You have been able to approach the star systems closest to our Earth. In this infinitely large space, an invaluable quantity of other systems remains to be discovered. Among those already listed, some are located at a short distance. Others, on the other hand, are several million light-years away. If for the majority of them, many similarities can be noted, for others one can distinguish an unusual composition. This is particularly the case for a system that is 150 light-years away from our galaxy, the system HD 98800, or TV Crateris. This one consists of 2 pairs of stars, distant from each other by 150 million kilometers or 93 million miles. I let you imagine what our sky would look like with 4 suns. But what makes it even more spectacular is the disk of dust that surrounds one of these 2 pairs. Another system, well known to all, also presents singular characteristics. It is Alpha Ursae Minoris, more often called Polaris. You know this star well under its common name of Polaris, easily spotted near the North Celestial Pole. It is the brightest star in the Little Dipper constellation. It is 431 light-years away from our Sun. But did you know that this star is in fact a multiple star? Polaris, which is a supergiant Cepheid variable, has in fact 2 smaller companions. It is thus a triple system. It has also been found 2 other components, even more distant. Half of the mass of the asteroid belt belongs to 4 objects: Ceres, Vesta, Pallas, and Hygiene. The total mass of the asteroid belt is about 4% of that of the Moon. Ceres is the only object in the asteroid belt large enough to be classified as a dwarf planet. It has a diameter of about 950 kilometers or 590 miles, while Vesta, Pallas, and Hygiene have an average diameter of less than 600 kilometers or 370 miles. The majority of the other bodies are the size of a dust particle. More than 200 asteroids are known to exceed 100 kilometers or 60 miles, and a study at infrared wavelengths has shown that the asteroid belt contains between 700,000 and 1.7 million asteroids with a diameter of 1 kilometer or more. The temperature of the asteroid belt depends on the distance of its objects from the Sun. For dust particles within the belt, typical temperatures range from minus 73 degrees Celsius or minus 99 degrees Fahrenheit at 2.2 astronomical units to as low as minus 108 degrees Celsius or minus 162 degrees Fahrenheit at 3.2 astronomical units. However, due to rotation, the surface temperature of an asteroid can change by solar radiation. Most asteroids in the asteroid belt have an orbital eccentricity of less than 0.4 of an inclination of less than 30 degrees. The orbital distribution of asteroids peaks at an eccentricity of about 0.07 and an inclination less than 4 degrees. Thus, although a typical asteroid has a relatively circular orbit and lies in the plane of the ecliptic, some asteroid objects can be very eccentric or extend well beyond the plane of the ecliptic. Sometimes the term main belt is used only to refer to the most compact central region. Thus, the limits are between the strong Kirkwood deviations between 2.06 and 3.27 astronomical units, and at orbital eccentricities lower than about 0.33, as well as at orbital inclinations lower than about 20 degrees. In 2006, this central region represents 93% of the minor objects discovered and numbered in the solar system. The astronomical database that lists the small bodies of the solar system, JPL Small Body, mentions more than 700,000 known asteroids of the main belt. The distribution of asteroids along the semi-major axis of their orbits is not random, as it has discontinuity. The asteroid belt creates a very active environment, where asteroid collisions occur frequently on astronomical timescales. A collision between major belt bodies with an average radius of 10 kilometers or 6 miles is expected to occur about once every 10 million years. The collisions may break the asteroid into several smaller pieces, leading to the formation of a new asteroid family. Conversely, collisions occurring at low speeds can, on the contrary, link two asteroids. Thus, in several hundred million years, the asteroid belt will no longer look like the one we know today. In addition to the asteroid bodies, the asteroid belt also contains dust bands whose particle size can reach several hundred micrometers. This material is formed, at least in part, as a result of collisions between asteroids and collisions of micrometeorites with asteroids. Due to the Poynting-Robertson effect, the pressure of solar radiation causes a slow spiral of this dust towards the Sun. The combination of this fine asteroid dust with the ejected cometary material produces the zodiacal light. This faint glow can be seen at night in the direction of the Sun, along the plane of the ecliptic. Asteroid particles emitting visible zodiacal light have an average radius of about 40 micrometers. The typical lifetime of particles in the main zodiacal clouds of the belt is about 700,000 years. Thus, in order to maintain the dust, new particles must be constantly produced within the asteroid belt. It was once thought that asteroid collisions were the main component of the zodiacal light. However, computer simulations have attributed 85% of the zodiacal light dust to fragments of Jupiter-like comets, rather than to comets and collisions between asteroids in the asteroid belt. Asteroids in the asteroid belt are classified according to their spectra, most of which fall into three main groups: C-type or carbonaceous asteroids, S-type rich or silicate asteroids, and M-type or metallic asteroids. The C-type or carbonaceous asteroids are, as their name indicates, rich in carbon. They dominate the outer regions of the asteroid belt. Together, they represent more than 75% of the visible asteroids. They are redder than other asteroids and have a very low albedo. Their albedo varies from 0.03 to 0.1, which means that they reflect only 3 to 10% of the incident light. Because of this, C-class asteroids are difficult to detect, so in reality, their share of the main belt may be well over 75%. Their surface composition is similar to that of carbonaceous chondrite meteorites. In chemical composition, their spectra correspond to the original composition of the primitive solar system, with the disappearance of the only lighter and volatile elements. In addition to carbon, these celestial bodies contain water, so they can be detected with observations in the infrared range. The largest asteroid of this class is Hygiene, whose diameter is estimated at 434 kilometers, or 270 miles. S-type asteroids rich in silicate, i.e. ordinary rocks, are more frequent in the inner region of the belt, within 2.5 astronomical units of the Sun. The spectra of their surfaces show the presence of silicates and some metals, but do not contain significant carbon compounds. This indicates that their materials have been considerably modified from their original composition, probably by fusion and transformation. They have a relatively high albedo that varies between 0.1 and 0.22. This category represents about 17% of the total asteroid population. The metal-rich M-type asteroids represent about 8% of the total population. They are mostly located in the center of the main belt. Their spectra resemble those of iron-nickel. It is thought that some of them were formed from the metallic cores of primitive bodies, differentiated and destroyed by the collision. The albedo of metallic asteroids is between 0.1 and 0.19, i.e., they have moderate reflectivity. It should be noted that scientists are not sure that metallic asteroids are made of metals because they are too thin. This means that either M-class asteroids have a similar composition to asteroids of other classes, or there are many cavities in their internal structure. However, there are also silicate compounds that can have a similar appearance. For example, the large M-type asteroid, 22 Calliope, does not appear to be composed primarily of metal. Within the asteroid belt, the distribution of M-type asteroids peaks at the semi-major axis, around 2.7 astronomical units. It is not yet clear whether all M-types have a similar composition, or whether this is a label for several varieties that do not fit into the main C and S classes. There are other rarer classes B, E, P, A, D, etc. Sometimes an asteroid cannot be strictly assigned to a single class. It is then considered to be of mixed type, which is indicated by two letters, for example, CG. One of the mysteries of the asteroid belt is the relative rarity of V-type asteroids that exhibit the properties of basaltic chondrites. Theories of asteroid formation predict that objects the size of Vesta or larger should form crusts and mantles that would be composed primarily of basaltic rocks, so that more than half of all asteroids should be composed of basalt or olivine. Yet observations show that 99% of the predicted basaltic material is missing. Until 2001, it was thought that most basaltic bodies found in the asteroid belt came from the asteroid Vesta, hence the name V-type. However, the discovery of asteroid 1459 Magnaya in 1937 showed that the chemical composition is somewhat different from other basaltic asteroids discovered until then. This hypothesis was reinforced by the new discovery in 2007 of two asteroids in the outer belt, 7472 Kumakari in 1992 and 10537 1991 RY16 in 1991. With different basaltic compositions that could not have come from Vesta. These last two are the only V-type asteroids found in the outer belt to date. Most of the asteroids are relatively small in size. In total, about 30 asteroids larger than 200 kilometers or 125 miles in diameter have been discovered. The largest objects in the asteroid belt are Ceres with 946 kilometers or 588 miles in diameter, Vesta with 525 kilometers or 325 miles in diameter, Pallas with 513 kilometers or 320 miles in diameter, and the asteroid Hygiea with a diameter of 434 kilometers or 270 miles. These four celestial bodies represent about half of the mass of the entire main belt. With Ceres considered as a dwarf planet, Vesta is thus the largest asteroid of the main belt. Moreover, Ceres is the only body in the asteroid belt large enough to maintain a spherical shape. Most asteroids are potato-shaped, although some take a more unusual shape. This is the case of asteroid 216 Cleopatra, which looks like a dog bone. Contrary to its representation in science fiction movies, the asteroid belt is quite spacious. It is so vast that the average distance between two asteroids is about 1 million kilometers or 600,000 miles. Thus, the probability of a spacecraft colliding with an asteroid is virtually zero. The material in the belt is so well distributed that many self-propelled spacecraft have passed through the belt without incident. However, collisions between large asteroids do occur and can lead to the formation of a family of asteroids whose members have different orbital characteristics and composition. In addition, the asteroids of the main belt are unevenly distributed. There are areas in which they are virtually absent. These areas, called Kirkwood gaps, are cleared of asteroids by the gravitational influence of Jupiter. On the other hand, some common bodies in the outer belt show cometary activity. Since their orbits cannot be explained by the capture of classical comets, it is thought that many other asteroids may be icy, sometimes sublimating, due to small impacts. The asteroid belt was discovered gradually during the 19th century. However, the area between Mars and Jupiter attracted the attention of astronomers long before that, with the aim of searching for a planet. The German astronomer Johann Kepler noticed in 1596 deviations in the orbits of Mars and Jupiter. He thought that there was too much deviation in these orbits, and he explained this by the presence of a planet in this region. Today, scientists explain these deviations as a result of the gravity of asteroids. In 1766, another German astrophysicist, Johann Daniel Titius, noticed an apparent pattern in the arrangement of the planets. He found a formula by which it was possible to calculate the approximate position of all the planets in the solar system. The principle of this formula was that the ordinal distance of the planets from the Sun increases exponentially according to the following hypothesis. Counting from the center of the solar system, each succeeding planet will be located about twice as far away as the planet before it. According to this hypothesis, known today as Titius-Bode's law, there must have been an as yet unknown planet between the orbits of Mars and Jupiter. In 1781, when William Herschel discovered Uranus, the orbit of the planet was almost exactly right according to the Titius-Bode law, which convinced many scientists of the truth of the law of interplanetary distance, and led astronomers to conclude that there must be a planet between the orbits of Mars and Jupiter. It was on January 1, 1801, that Italian astronomer Giuseppe Piazzi discovered the first asteroid, Ceres, in this region of the solar system. From this discovery, scientists believe that Ceres was the famous lost planet. Soon, other similar objects were discovered in the same region of the solar system. As scientists discovered more and more celestial bodies between Mars and Jupiter at an increasing rate, it became more and more difficult to count them as planets. Thus, these bodies were removed from the list of planets, and Herschel's choice of nomenclature, i.e. asteroids, gradually came into effect. One interesting fact put the Titius-Bode law in check. When Neptune was discovered in 1846, it turned out that its location did not match Titius's predictions. Apparently, the Titius-Bode law is nothing more than a mathematical coincidence, and not a physical law at all. To this day, there is no scientific explanation for this law, and according to astronomers, it is a coincidence. In 1868, about 100 asteroids were discovered, and an astrophotograph by the German astronomer Max Wolf was made later. A total of 1,000 asteroids were discovered in 1921, 10,000 in 1981, and 100,000 in 2000. Modern asteroid exploration systems currently use automated means to discover new asteroids and minor planets in ever-increasing numbers. The asteroid belt has been of interest to scientists not only in past centuries but also in recent years. Since the 1970s, several spacecraft have been able to reach the asteroid belt and study its objects. The first achievement of modern technology in the study of this cluster of celestial objects was the flight of the American space probe Pioneer 10, designed to study Jupiter, which entered the region on 16 July 1972. This spacecraft was the first to cross the asteroid belt. Since then, 9 other spacecraft have crossed the belt. At the time, it was feared that debris in the belt could pose a danger to a spacecraft, but 12 spacecraft have since crossed without incident. The Pioneer 11, Voyager 1 and 2, and Ulysses spacecraft have crossed the belt without obtaining images of asteroids. Other missions, including Galileo, Near Shoemaker, Cassini, New Horizons, and Rosetta, have photographed some asteroids. The Galileo spacecraft was the first spacecraft to take pictures of asteroids. It studied the S-type asteroids 951 Gaspra in 1991 and 243 Ida in 1993, and discovered for the first time an asteroidal moon of 1.4 kilometers in diameter, orbiting the asteroid 243 Ida. The space probe Near Shoemaker was launched in 1996, and in February 2000, it entered the orbit of asteroid 433 Eros. Thus, it was possible to study in detail its chemical composition, as well as to build a three-dimensional model of a celestial body. In 2001, the probe landed on Eros and explored for 2 weeks its soil to a depth of 10 centimeters. Once these images were obtained, NASA decided that any spacecraft flying near the asteroid belt should try to take pictures of these objects. In 2003, the Japanese probe Hayabusa was launched. It explored the asteroid 25143 Itokawa. The device was able to collect soil samples from this asteroid and send them to Earth. The Dawn mission was the first to visit the asteroids Vesta in 2011 and Ceres in 2015. Thanks to this mission, nearly 69,000 photographs of these asteroids and many other data were obtained. On the other hand, on its way to Jupiter, the Juno spacecraft crossed the asteroid belt without collecting scientific data. Because of the low density of material in the belt, the chance of a probe colliding with an asteroid is now estimated to be less than 1 in 1 billion. Most images of asteroids in the belt have been obtained from brief flybys by probes aimed at other targets. Only the Dawn, Near Shoemaker, and Hayabusa missions have studied asteroids for extended periods in orbit and on the surface. NASA's Psyche spacecraft is scheduled to launch in October 2023. It is scheduled to set out to discover asteroid 16 Psyche. Scientists suggest that this asteroid is composed of a core of iron, nickel, and gold. Initially, scientists thought that the asteroid belt was formed as a result of the destruction of a hypothetical large planet, which according to the Titius-Bode law should have been orbiting between Mars and Jupiter. The planet was named Phaeton, after the son of the ancient Greek sun god Helios. However, calculations simulating the destruction process of Phaeton did not confirm this hypothesis. It should be noted that many astrophysicists around the world supported the hypothesis of the collapsed planet until the end of the 20th century. In fact, the amount of energy required to destroy a planet, coupled with the combined mass of the asteroid belt, which is only about 4% of the mass of our moon, as well as the major chemical differences between the asteroids, does not support this hypothesis. In 2018, a study by scientists at the University of Florida found that the asteroid belt was created from the remains of several protoplanets, not a single planet. This research supports the hypothesis that the asteroid belt was formed about 4.6 billion years ago from the primordial solar nebula by small clumps of cosmic dust called planetesimals, the smallest precursors of protoplanets, which form during the accretion process. Over several million years, the accretion process caused small particles to stick together and gradually increase in size. When the clusters reached a sufficient mass, they could attract bodies by gravitational attraction and become planetesimals. Some of these planetesimal bodies eventually became the planets we know today. At the dawn of the asteroid belt's formation, the planetesimals were too disrupted by Jupiter's gravity to form a planet. Instead, they continued to orbit the Sun as before, colliding from time to time. In regions where the average impact rate was high, planetesimal destruction tended to outweigh accretion, preventing the formation of planet-sized bodies. In fact, orbital resonances were activated when the period of an object in the belt was part of the orbital period of Jupiter, placing the object in a different orbit. The region between the orbits of Mars and Jupiter creates many of these orbital resonances. Thus, the orbits of asteroids are violently perturbed whenever their period of revolution around the Sun forms an orbital resonance with Jupiter. At these orbital distances, a Kirkwood gap occurs when they move to other orbits. Recall that the Kirkwood gap represents the deviation in the distribution of the semi-major axes, or orbital periods of the orbits of the main belt asteroids. They correspond to the locations of the orbital resonances with Jupiter. In the region of the solar system between Mars and Jupiter, the gravital perturbations of Jupiter have endowed the planetesimals with too much orbital energy to be captured and agglomerated to form a planet, dynamically exciting these bodies and increasing their velocity relative to each other. The collisions became too violent, and instead of merging, the planetesimals and most of the protoplanets were reduced to small pieces. In the early days of the Earth's existence, asteroids underwent some degree of melting. Some asteroids may even have experienced periods of explosive volcanism and emitted magma. Nevertheless, because of their relatively small size, the melting period was necessarily short, compared to much larger planets, and generally ended within the first tens of millions of years of the solar system's formation. In August 2007, the study of zircon crystals in an Antarctic meteorite, believed to have come from Vesta, showed that it, and by extension the rest of the belt, formed quite rapidly, within 10 million years of the formation of the solar system. The current asteroid belt is thought to contain only a small fraction of the mass of the original belt. Computer simulations suggest that the primary asteroid belt could have had a mass equivalent to that of the Earth. Primarily due to gravitational disturbances, most of the material was ejected from the belt during the first million years of its formation, leaving less than 0.1% of its original mass. As a result, 99.9% of the original mass of the asteroid belt was lost during the first million years of the solar system's history. Some of the fragments ended up in the inner solar system, causing meteorite impacts on the inner planets. Since the formation of the belt, the size of the asteroids has remained relatively stable. They have not increased or decreased significantly. The 4-to-1 orbital resonance with Jupiter at 2.06 astronomical units from the Sun can be considered the inner limit of the asteroid belt. Jupiter's perturbations send deviating bodies into unstable orbits there. Most of the bodies formed within the radius of this space were captured by Mars, which has an aphelion of 1.67 astronomical units, or rejected by its gravitational disturbances early in the history of the solar system. When the asteroid belt first formed, the temperature at a distance of 2.7 astronomical units from the Sun formed a snow line below the freezing point of water. Therefore, planetesimals formed outside this radius were able to accumulate ice. In 2006, a group of researchers reported that a population of comets had been discovered in the asteroid belt beyond the ice line, which may have provided water to Earth's oceans. According to some models, the outgassing of water during the formation of the Earth was not sufficient to form the oceans, an external source, such as cometary bombardment, would have been necessary. Scientists have drawn attention to the heterogeneity of the composition of the asteroid belt. The silicate-type asteroids, similar in their properties and composition to the terrestrial planets, are located in the inner ring, and the carbon-type asteroids, on the contrary, approaching the composition of giant planets, are in the outer ring. According to astrophysicists, this may indicate that asteroids were formed as debris during the genesis of other planets, after which they were projected into the region between Mars and Jupiter, where they are currently located. To confirm the proposed hypothesis, the scientists simulated the process of planet formation from a disk of gas and dust, and verified the possibility of planet formation from debris that migrates to the giant planets and concentrates in a certain area. The formation of each of the 4 planets was modeled separately, taking into account the gravitational influence of Jupiter and Saturn with a corresponding orbital resonance. By gathering all the data, the scientists received information about the possible distribution of silicate asteroids, and after further studying the growth mechanism of gas giants, the scientists came to the conclusion that gas accretion could lead to destabilization of their orbits and subsequent ejection of carbon-like asteroids into a region closer to the Sun. Based on the data obtained, the scientists estimated the inclination and eccentricity of the resulting fragments' orbits and came to the conclusion that the mechanism they proposed could indeed lead to the formation of the asteroid belt in its modern form. Thus, most likely, the asteroid belt immediately formed in its present, rather sparse form, with a small mass and a heterogeneous compositional distribution. The ability to simulate the process of planet formation is leading to the emergence of new hypotheses about the origin of objects in the solar system. For example, scientists have recently proposed a new scenario for the formation of Mars, which probably formed right at the current location of the asteroid belt. Today, scientists know that the asteroid belt is by no means a broken planet, but that it formed from the remnants of protoplanetary material that appeared at the origin of the solar system. Ceres is the largest object in the main asteroid belt that lies between the orbits of Mars and Jupiter. With a diameter of 946 kilometers or 588 miles, Ceres is both the largest asteroid and the only dwarf planet in the asteroid belt. Ceres was the first asteroid discovered by Giuseppe Piazzi at the Palermo Astronomical Observatory on January 1, 1801. It was originally thought to be a planet, but was reclassified as an asteroid in the 1850s after the discovery of many other objects in similar orbits. The International Astronomical Union decided in 2006 to classify Ceres as a dwarf planet, alongside its primary status as an asteroid. Ceres is a surviving protoplanet, a sort of planetary embryo, formed 4.56 billion years ago. The only one preserved in the inner solar system, while the others have either merged to form telluric planets, broken up, or have been ejected from the solar system by Jupiter. Ceres formed as a centaur, a small body in the solar system, with either a perihelion or a semi-major axis between those of the outer planets, most likely between the orbits of Jupiter and Saturn, and was scattered in the asteroid belt when Jupiter migrated slightly inward from the solar system. Ceres follows an orbit between Mars and Jupiter, inside the asteroid belt and closer to the orbit of Mars, with an orbital period of 4.6 Earth years. Ceres is an orbital resonance of mean motion, close to 1:1, with the asteroid Pallas. but a real resonance between them is unlikely because of their small masses compared to the large distances between the asteroids. Such relationships are rare. The rotation period of Ceres is 9 hours and 4 minutes. It has an axial tilt of 4 degrees. This is low enough that Ceres' polar regions contain permanently shaded craters, which should act as cold traps and accumulate water ice over time, as on the Moon and Mercury. Ceres is the only object in the asteroid belt that is surrounded by its own gravity, although Vesta and perhaps other asteroids have been in the past. Even at maximum brightness, it is too faint to be seen with the naked eye, except under extremely dark skies. Ceres has been classified as a C-type asteroid, and due to the presence of clay minerals as a G-type asteroid. Ceres represents about 1/3 of the total estimated mass of the asteroid belt, or 1.3% of the mass of the Moon. Its surface area is about the same as that of India. Modeling has shown that Ceres may have a small metallic core due to the partial differentiation of its stony fraction. The surface of Ceres is homogeneous and rich in carbonates and ammoniacal phyllosilicates altered by water. The ocean of water thought to have existed early in Ceres' history must have left a layer of ice beneath the surface when it froze. The fact that the Dawn spacecraft found no evidence of such a layer suggests that Ceres' original crust was at least partially eroded by later impacts, carefully mixing ice with salts and ancient silicate-rich seafloor material below. Ceres' surface is hot enough for the surface ice to sublime. The sublimation material could explain Ceres' dark surface compared to icy moons in the outer solar system. Studies by the Hubble Space Telescope indicate that graphite, sulfur, and sulfur dioxide are present on the surface of Ceres. The former is obviously the result of cosmic weathering of Ceres' ancient surfaces. The latter two are volatile and should either escape quickly or be deposited in cold traps, and are apparently associated with areas of recent geologic activity. Scientists have identified 22 ancient cryovolcanoes on Ceres, ranging from 16 to 86 kilometers, or 10 to 53 miles wide, and 1.1 to 4.4 kilometers, or 0.6 to 2.8 miles high. Cryovolcanoes form about once every 50 million years. In August 2020, NASA confirmed that Ceres is a water-rich body with a deep reservoir of brine, which leaks to the surface in various places, causing bright spots. There are indications that Ceres has a thin atmosphere of water vapor emanating from the water ice on the surface, making it an active asteroid. Surface water ice is unstable at distances less than 5 astronomical units from the Sun, so it should turn to vapor if exposed to direct solar radiation. Water ice can migrate from deep layers of Ceres to the surface, but it will then evaporate in a very short time. On January 22, 2014, ESA scientists reported for the first time the discovery of several sources of water vapor at mid-latitudes. The exploration was carried out using the space observatory Herschel. This was unexpected because large bodies in the asteroid belt do not normally emit vapor, which is a characteristic of comets. Possible mechanisms for vapor release are sublimation from exposed surface ice or cryovolcanic eruptions resulting from internal heat or increased pressure in the subsurface layers of the ocean due to the growth of overlying layers of ice. In 2017, Dawn confirmed that Ceres has a transient atmosphere that appears to be related to solar activity. The ice on Ceres can sublimate when energetic particles from the Sun strike the ice inside the craters. Although the hypothesis of a potential microbial home for extraterrestrial life is not discussed as much as for Mars, Europa, Enceladus, or Titan, there is evidence that the icy mantle of Ceres was once a watery subsurface ocean. It appears to contain up to 20% carbon by mass in its near surface. Indeed, carbon-rich compounds are intimately mixed with the products of rock-water interactions such as clays and can create conditions favorable for organic chemistry. This is the largest asteroid in the belt. Its average diameter is 525 kilometers or 326 miles, and its mass is estimated at 9% of the mass of the main belt. It is the only asteroid that can be observed without a telescope or binoculars, as it reflects 42% of the sunlight. Vesta's orbit crosses the interior of the belt. It is located in the main Kirkwood Gap. The orbital period of the asteroid Vesta around the Sun is 3.6 years. This asteroid has a rather important asymmetry. If its shape were more spherical, then Vesta could be classified as a dwarf planet. Unlike many other asteroids, a complex geological history is visible here. The core is composed of nickel and iron, while the mantle is composed of rocks. Over time, the core and mantle have melted and crystallized. These phenomena have resulted in a large amount of minerals. The current distance between the asteroid Vesta and the Sun is 2.2 astronomical units. The rotation of the asteroid around its axis is 5.3 hours, and the axis is tilted by 29 degrees. Although temperatures on Vesta fluctuate throughout the year, the model predicts that the average annual temperature near Vesta's north and south poles is less than -128 degrees Celsius, or -198 degrees Fahrenheit. Near Vesta's equator, however, the average annual temperature is about -123 degrees Celsius, or -189 degrees Fahrenheit. It is assumed that many of the small objects surrounding the asteroid are parts of Vesta that have broken off as a result of collision with other planets. This asteroid has a huge crater near its south pole. It was formed in a collision that created a whole family of asteroids moving near it. Pallas was the second object discovered in the asteroid belt. It represents 7% of the mass of the main belt, with an estimated diameter of 513 kilometers or 320 miles. In terms of both size and mass, Pallas ranks third among the main belt objects, just behind Ceres and Vesta. In 2006, Pallas was considered a candidate for the title of dwarf planet. But due to its shape, which is too different from the spherical shape, astronomers consider it unequivocally as an asteroid. Pallas moves in an elliptical orbit around the Sun, so the distance between these two bodies is not constant. The minimum distance between this asteroid and the Sun is 2.1 astronomical units, while the maximum distance is 3.4 astronomical units. In addition, the revolution of Pallas around the Sun lasts 4.6 Earth years. The orbit has a large inclination to the plane of the ecliptic, which is 34.8 degrees. For other large asteroids, this inclination is less than 10 degrees. The asteroid also rotates on its own axis, making a revolution every 7.8 hours. The average speed of Pallas on its orbit is 17.6 kilometers per second, or 11 miles per second. There is a 1-to-1 resonance between Pallas and the dwarf planet Ceres. This means that their periods of revolution around the Sun coincide. The albedo of Pallas, i.e. the proportion of reflected light, is 15%. Such reflectivity, as well as its large size, make Pallas one of the brightest objects in the asteroid belt, but it cannot be seen with the naked eye. According to its spectrum, Pallas belongs to the carbon group asteroids, or C group. This means that Pallas is dominated by anhydrous silicates, sulfides, and magnetides. It also contains polymers. The asteroids of this class have a bluish spectrum, and they almost do not absorb light with a wavelength below 500 nanometers. There is a whole family of Pallas, that is to say, a group of asteroids which are probably fragments formed during the collision of Pallas with another celestial body. All the asteroids of this family belong to the same class, and their orbits are distinguished by a strong inclination. But none of these asteroids is a moon of Pallas. Little is known about the relief of Pallas today, since it is studied only with telescopes. Near the equator is a crater that was formed more than 1.7 billion years ago during a collision with a meteorite with a diameter of 40 kilometers or 25 miles. Due to the steep inclination of the orbit, greater than 34 degrees, Pallas is very difficult to explore with spacecraft. However, in 2024, the launch of the mission Psyche is planned, within which an auxiliary flight of the probe Athena towards Pallas is possible. It is the fourth largest asteroid, with an estimated diameter of 434 kilometers or 270 miles, and the 10th object discovered in the asteroid belt. For a long time, High-G was thought to have an irregular shape. Only observations in 2017 showed that in fact, the asteroid's shape is close to spherical. This means that one day, High-G could be recognized as a dwarf planet. It represents 3% of the mass of the entire belt. The average surface temperature of High-G is minus 109 degrees Celsius, or minus 164 degrees Fahrenheit. It is an asteroid with an albedo of 0.07, so its surface is very dark, reflecting only 7% of the sunlight that falls on it. The darkness of High-G's surface is due to the fact that it belongs to the so-called C-class asteroids, in which carbon predominates. Moreover, High-G is the largest representative of this class. The chemical composition of these asteroids is close to that of the chondrite meteorites, which fall most often on the Earth. It is also assumed that the protoplanetary cloud had approximately the same composition, from which the planets of the solar system were formed 4.5 billion years ago. High-G, like the other asteroids, has an elliptical orbit. The maximum distance between this asteroid and the Sun is 3.5 astronomical units, while the minimum distance is 2.77 astronomical units. High-G takes 5.5 years to complete one revolution around the Sun. The orbit of the asteroid has a slight inclination to the plane of the ecliptic, equal to only 3.8 degrees. It is only in 2018 that scientists have managed to estimate the period of revolution of High-G around its own axis. It is equal to 13.8 hours. In his case, the direction of rotation could not be determined reliably. Calculations show that the orbit of High-G is unstable, so it will change chaotically due to the effect of the gravity of Jupiter and Saturn on the asteroid. It also has its own family of asteroids formed by the collision of High-G with another celestial object. Computer simulations show that during this collision, High-G was completely destroyed, but over time, most of the fragments reconnected to each other under the influence of gravity. It is not surprising that asteroids can collide with the Earth, and if this had not happened very often in the past, we probably would not exist today, because most of the water on our planet came from asteroids and comets. Planets form from a large disk of gas and dust. The inner regions of this disk are close to the star and are usually very hot. Water and other volatile substances evaporate from them. Thus, the disk appears to be dry inside, and it is in these inner regions that Earth-like planets form. So by default, there should be relatively little water. The same thing happened with our Earth. The water or water vapor involved in its formation slowly rose to the surface over time as a result of volcanism. But this was clearly not enough. Most asteroids form behind the so-called ice line. The ice line is an isothermal line that represents the limit beyond which it is cold enough for water in the form of ice to be part of the celestial bodies that form from the protoplanetary disk. In our solar system, the ice line crosses the asteroid belt between the orbits of Mars and Jupiter. This is why most asteroids contain a lot of frozen water. These asteroids often collided with the Earth in ancient geological times. This is how a large amount of water arrived on our planet. But asteroids could bring not only water, but also something more. Some scientists suspect that perhaps the first complex molecules, the first building blocks of life, arrived on Earth carried by asteroids. And it could even be argued that asteroid impacts, such as the one that occurred 66 million years ago, notably extinguishing the non-avian dinosaur kingdom, spurred evolution and forced it to take a new direction. Without the collision that took place 66 million years ago, mammals, and therefore humans, would certainly not have become the dominant class on this planet. Therefore, it is fair to say that asteroids are an important factor in the emergence of terrestrial life. The presence of this asteroid belt in the inner solar system is closely associated with Jupiter. This gas giant grew faster than any other planet during its formation, and eventually became the largest planet in the solar system. Because of its large size, Jupiter's gravitational disturbances could have prevented the formation of a planet in its vicinity. This is why there are no other large celestial bodies between Mars and Jupiter, only asteroids. If Jupiter had formed farther from the Sun, the asteroid belt would have been farther away as well, like the Kuiper belt, and the asteroids would have had little chance of colliding with the Earth. If Jupiter had been closer to the Sun, the region would have been warmer, and the asteroids would not have contained ice. Another very interesting fact is the motion of Jupiter around the Sun. In fact, its path of motion has been constantly changing. Astronomers call this phase of the solar system's development planetary migration. When Jupiter migrated, it slightly touched the asteroid belt. Thus, many asteroids were expelled from the solar system, or were destroyed. This event has its importance, since it signs the beginning of the Great Late Bombardment. Its estimated duration is 50 to 150 million years, centered on 3.9 billion years. The rate of bombardment is estimated to be 20,000 times that currently observed on Earth, which corresponds, for example, to an impact of an object of more than 1 kilometer every 20 years, allowing a water supply. Thus we see that the solar system needed not only a large planet that forms in the right place, beyond the ice line, but also a planet that could migrate in the right direction. Astronomers don't yet know enough details about other planetary systems to know if the situation there is similar to ours, but the current data are not very encouraging. However, scientists have the opportunity to analyze the available data and find out how many large exoplanets are in front of or behind their ice lines. Recently, research has shown that most exoplanets are not in the position needed to create the right asteroid belt. But the importance of these research results should not be exaggerated, since we are talking about planets close to their star that are not easy to detect. It is only when astronomers discover many more extrasolar planets that it will be possible to be more affirmative. And here again, the problem of migration arises. It was already difficult enough to establish the exact nature of migration in our solar system. This is even more difficult to do with extrasolar planetary systems. However, if we want to study the dynamics of planetary motion with sufficient precision, we must look into this question. It is very interesting to observe how complex the interactions of the components of the planetary system can be. Small rocks, interplanetary dust particles, comets, and everything else also play an important role. All the bodies influence each other, and all of them have allowed life to appear on our planet. Many craters on the surface of the Moon, Mercury, and other solar system bodies are often used to illustrate the danger that asteroids represent for the Earth. However, it should be remembered that the vast majority of these craters were formed during the late bombardment period. On the surface of the Earth, thanks to modern technologies, including the analysis of satellite images, it is possible to detect traces of collisions with asteroids, which belong to much later periods in the evolution of the solar system. The largest and oldest known crater is the Vredefort Dome, which is located in South Africa. Its diameter is about 250 kilometers or 155 miles. Its age is estimated at 2 billion years. The Chicxulub crater on the coast of the Yucatan Peninsula in Mexico was formed after an asteroid impact 66 million years ago, equivalent to the energy of an explosion of 100 teratons of TNT. With a period of high volcanic activity, this event signed the famous extinction of the non-avian dinosaurs, causing tsunamis, earthquakes, and climate changes due to the layer of dust formed in the atmosphere that obscured the sun. One of the most recent craters is the meteor crater from a large iron asteroid of 30 to 50 meters in diameter that hit the Colorado Plateau in northern Arizona with a mass of several 100,000 tons 49,000 years ago. In total, there are now about 170 impact craters formed by falling celestial bodies. The event near Chelyabinsk in Siberia attracted the most attention when on February 15, 2013, an asteroid entered the atmosphere in this area, which was estimated to be about 17 meters or 55 feet in size and 13,000 tons in mass. It exploded in the air at an altitude of 20 kilometers or 12 miles, its largest part weighing 600 kilograms, or 370 miles, fell into Lake Chebarkul. The energy of the explosion was equivalent to 0.5 megatons of TNT, which corresponds to 30 bombs dropped on Hiroshima. The Chelyabinsk asteroid became the most detailed event of this magnitude after the explosion of the Tunguska meteorite on June 30, 1908. According to modern estimates, the fall of celestial bodies, such as Chelyabinsk, in the world occurs about once every 100 years. As for the Tunguska event, trees were burned over an area with a diameter of 50 kilometers or 30 miles. Such disasters occur about once every 300 years.